హలో రమణ గారు సార్.
సార్ చెప్పండి. ఎస్
సార్
సార్.
యాక్చువల్లీ యూ షేర్ యువర్ స్క్రీన్ సార్.
బట్ ఇట్ ఇస్ నాట్ అలవింగ్. వెయిట్.
యాక్చువల్లీ జస్ట్ ఐ క్లెయిమ్ ది హోస్ట్ ఇన్ ఆర్డర్ టు రికార్డింగ్ పర్పస్ అగైన్ ఐ మేక్ యూ హోస్ట్ సార్. దట్స్ వై. ఓకే సార్.
కమింగ్.
ఎస్ సార్, కటింగ్ సార్.
ఫుల్ స్క్రీన్ ఇస్ కమింగ్.
ఎస్ సార్, ఎస్ సార్.
ఇస్తారా ఎవరికి ఇస్తారా?
సునీత ఎవరైనా ఇచ్చేస్తుంది.
Sir, okay, sir.
We'll start, sir, or we have to wait, sir?
No, sir, we can start, sir. We can start. Sir.
Otherwise, we have to wait. Some people can join otherwise.
Okay, sir. Okay, sir. By 6:10 we will start, sir. Then.
Okay. 6:05, 6:10. Okay.
Okay, sir. Okay, sir.
Sir, screen is visible, no?
Yes, sir.
Screen.
Yes, screen is visible, sir.
Screen is for only presentation screen only, no?
Yes, sir. Presentation screen only, sir.
Not other screens.
No, sir. Sir. Actually, whatever whatever you are displaying, we are seeing, sir. Antennas for EMI, EMC
Okay.
measurements.
That's only, no? Not remaining windows.
No, sir. No, sir. Remaining, not many windows. Sir, I'm going to read your profile, sir.
Pardon, sir? Video.
I'm going to read your profile, sir. I'm going to
Okay.
share your profile to the participants.
Hmm.
Good evening, everyone. I'm myself, G. Sivasuresh Kumar from Vignan Institute of Engineering for Women. Today we are going to have the third day. In this today's session, our research person is Mr. Sri B. Venkat Ramana garu, who is scientist D. He is working in Samir Center for Electromagnetic Environment Effects in Visakhapatnam, Ministry of Electronics and Information Technology, Government of India. He is the senior member of IEEE EMC Society, life member of SENMCE 1, and as per the today's session, he is going to give a brief about the antennas for EMA-EMC measurements, and I'm going to read it out. And I'm going to read some of his uh, key lifetime achievements, and I'm going to share with you as being a participant. Okay. Uh, uh, Sri B. Venkat Ramana garu received his BTech degree in ECE engineering with first class distinction from JNT Kakinada in 2010. In 2012, he joined Samir Center for Electromagnetics in Chennai, India, as a scientist, where he specializes in EMC testing, measurements, design consultancy, and the evaluation of electrical and electronic equipment in accordance with national and international standards. In 2014, he moved to Samir's Center for Electromagnetic Environment Effects, E3, in Visakhapatnam, where he established a highly specialized high-power electromagnetic facilitates India's largest electromagnetic pulse facility, PCI, UWB, MIL testing, and 3D EM modeling to support Indian industries. He is an expert in EMP and electromagnetic interface and electromagnetic compatibility, and he has evaluated multiple defense systems developed by DRDO and tri-services for EMC compliance. Venkat Ramana garu has received two Best Research Paper Awards for his contributions at INCEMIC 2018 and GEMCCON 2019, and has published over 25 scientific papers in prominent IEEE, IEE journals and international conferences. He completed his master's degree in RF and microwave with first class distinction from Andhra University in 2021. He is a he is a senior member of IEEE and has served as an executive member of IEEE EMC Society Madras chapter. Additionally, he is a lifetime member of SEMCEI India. His research interest includes EMA-EMC, high power electromagnetics, electromagnetic modeling and analysis, and HEMP mitigation and hardening methodologies. Thank you. Thank you, participants. Thank you very much, sir. You gave me opportunity to know our participants to know about you, sir. Thank you very much, sir. And we very much delighting to listen your session, sir.
Okay. So can we start?
Yes, sir. Sure, sir.
So thank you, Vignan Institute of Engineering for Women, WISAC, to invite me as a resource person to deliver a lecture on antennas, as it is 5G antenna technology development on recent trends in VLSI technology. So thank you, Vignan College, for inviting me as a resource person. So today I would like to deliver about antennas which are used in EMMC measurements, and also due to miniaturization of these antennas while going advanced VLSI technologies for 5G, 6G communications. So when it is going towards miniaturization, the effects of EMI point of view, EMI effects in miniaturization also I will cover in this topic. So before that, I would like to introduce about these topics. One is various basics of EMMC, because without understanding EMMC, the antennas used in EMMC cannot be understood, and typical EMC antennas and applications of EMC antennas, and some of the modeling and simulation analysis of various antennas and EMC principles, and EMC aspects in miniaturization of the antennas and circuits. So what are the EMC aspects we need to consider in miniaturization for going towards various advanced antennas like 5G, 6G, and few facilities introduction at last for understanding the few of the like members may not possible to visit our campus, so they can visualize our facilities through remote mode. So later, if anything opportunity comes, they can visit also. So let's move on to the first topic, EMMC. So what is EMI? What is EMC? So EMI is a operation disruption of a device, electronic device, either electrical electronic device, operation disruption when is in the vicinity of electromagnetic field, which is created by itself or due to other equipment. So you have a two equipments, you assume. One equipment is creating one electromagnetic environment. One electronic equipment is creating electromagnetic RF disturbance. The nearby equipment should not disturb. It has to be satisfactorily work. Then only there is no electromagnetic interference problem. So the interference is a disruption of operation of electron device when it is in the electromagnetic environment vicinity of that device. So like for example, if you have a TV, if you have interference, the image will be blur. If it is a normal, it will have no interference. So we can see visualize in the TV reception. But in electronic systems, we cannot visualize, but the functionalities of the devices can be vary. Whether it can be triggered, it can be wrong response, it can be sometimes catastrophic. So based on the level of intensity of the electromagnetic disturbance, that can be characterized as various phenomena like problems. So EMI, once. So the EMI electromagnetic interference, it can be from a equipment or to a equipment. If we assume it can be like if you take simple electronic equipment, it can come from through wired mode or it can be come through wireless mode. So it can be radiation into a product or radiation from a equipment, either radiation from a panel components. So it can be coupled either two ways, not in one way. So I would like to indicate that concept. So this is the EMI situation model. So whenever these three elements are present, then there will be a EMI problem. Source or emitter or culprit. These are the synonyms. Source is a where electromagnetic signal is generating. It can be intentionally generated or unintentionally generated. When it is generated intentionally, broadcasting stations, various communication transmissions, or any other is the intentional transmissions. Unintentional transmission means whenever any electronic motors are running or any electromagnetic induction like inductive operations are going on, when it is operation, the noise will be reflected when any switching operations are taking place. So these are all unintentional electromagnetic sources. So when intentional and unintentional source is taken place, and nearby product is the receiver, and coupling path is the medium. From this equipment to other equipment, the coupling path, it can be medium or a wire or wireless medium. So if you assume source is available, coupling path is available, receptor is available. In theory, if you eliminate any one of these elements, for example, if you eliminate coupling path, there is no coupling from source to a receiver, then no EMI. If you eliminate receiver, then no one is receiving. How much source it can generate, not an issue for the receivers. If you eliminate source, when the source is not there, as like coronavirus is not there, nobody will react. So if you eliminate any one of these element, there is no EMI. But in practically, it cannot possible to eliminate all these things. Only we can make it their effects. Source can be minimized. Instead of radiating this much radiated power, we can minimize. And receiver can make it more susceptible, more immune. Like if any electromagnetic signal comes also, I can make it my circuit. My circuit can be more threshold. I can tolerate some level. And coupling path from source to victim, the coupling path can be made as inefficient as possible. If you make efficient coupling path, complete source will go to the receiver. So receptor. So if an inefficient as possible, if you make it, no, inefficient means it cannot carry the information from source to receiver, then EMI coupling will be minimized. But if you make as inefficient as possible, your desired signal also sometimes it may efficiency will come decrease. So we need to take care of efficiency of your wanted signal as inefficiency for the EMI signal. So this design also, these points also we need to be considered while handling the EMI situation. So this is the simple EMI situation model. This has to be considered while designing. So these are the various EMI sources. It can be comes through naturally or man-made. If it is a natural, either nuclear detonation or any naturally disturbances, either solar storms or whatever it can be terrestrial or extraterrestrial. Man-made means wherever any industry is there, power electronic industry, there is a power electronic systems operation, EMI signal will be generated, electronic communication systems, machines and tools, various welding machines, various machine systems which are operating, a sudden change of voltage or current will happening, dV by dt, di by dt. That changes of current voltage sudden will indicate some pulse. That pulse corresponds to the broad spectrum. The spectrum corresponding to various frequencies couplings to the nearby equipments. And ignition system, consumer and medical electronics, and nuclear. In consumer also various electronic devices are now, as we are completely relying on technology on electronics development, we are more vulnerable to this type of electromagnetic disturbances. So that has to be considered. These are the sources of various EMI sources. If you go to the receptor, other side, receptor means who is receives the electromagnetic energy. So naturally, we are also receiving animals, plants. So at what level, that can be again separate subject. And man-made and communication receivers, we have a communication receivers for various applications, navigation, radar, broadcast, various, and industrial applications, various sensors are there, computers, advanced computers, controllers, and consumer and medical, various public addressing systems, biomedical systems, and ordnance, if you emitting diodes and fuels, various, wherever you go, there is electronic system, there is a EMI problem. So we need to consider each and every sector for EMI receptor, EMI evolution. So whenever source is there, every electronic equipment also possible to receive electromagnetic disturbance, that has to be properly handled such that our system cannot be disrupt the operation. It has to be properly operated. So EMI again two types, inter-system EMI, intra-system EMI. Inter-system means between two systems. If you observe here, one command control room is there. On that, various electromagnetic disturbances are coming. So power line disturbances are coming, lightning disturbances are coming, TV radio broadcasting disturbances are coming, ship communication disturbances coming, radar, walkie-talkies, ignition, all. So other way, from command control room to again reverse. It is going to the power lines. It is going to the airplane communication while operation and television communication. So EMI can be variety of electromagnetic disturbance sources, not single one. It can be various categories. If you see here, various power line, lightning, natural, intentional, unintentional. So various disturbances will come. So we need to be design our circuits carefully to guarantee electromagnetic compatibility of our environment. Electromagnetic compatibility of the equipment operation has to be taken care. For that, careful design is required. If you design for only one treatment, for example, you are considered only S-band communication. So then it has to be taken care of power line communication and also some wireless communication. Each and every category also we have to be taken care. So intra-system, within the system, if this is simply a receiver circuit, antenna is there, it is receives the signal and RF amplifier, mixer, local oscillator, mixer, IF amplifier, detector, simple receiving circuit. So complete receiving circuit is shared with common impedance coupling path. That means the ground of the all circuits are common impedance. So whenever it is common impedance, so one circuit to other circuit, it is having some wire length, that wire offers some resistance. So whenever current is coming here, it has to go to ground ideally, but wire is offering some impedance. So that impedance is some value is there, voltage is developing because of this ground current. That voltage again either adds up or subtracts. So when it is making some voltage drop across the ground, it is propagated along the ground. It may couple to the other circuit which is commonly shared by the same ground. That means ground should be ideally zero impedance. It has to be, any signal comes, it has to be sync. It has to be swallow. It has to be taken into its neutralized. It is zero potential. When it is zero impedance means potential is zero. But ideally it's not possible. Some practical wires we are using. So that wire itself, it is having some resistance, it is developing some voltage. That voltage is commonly shared by all the circuits. It will couple through common impedance coupling. Similarly, two circuit wires are side by side. If you assume here, these two circuit wires are side by side. So when both wires are side by side, mutual inductance will take place. So one conductor carrying some current, other conductor carrying some other current. Due to this current, mutual self-inductance, some magnetic field is creating around the wire. This magnetic coupling will be coupled to the other conductor. Similarly, two wires are separated by particular distance. Again, it will create some electric field between these two wires. Electric field coupling will take place. So whenever any wire is passing from one component to other component, one circuit to the other circuit, so we need to properly address the routing of the cables such that no EMI problems will be addressed at our final design. And this is the coupling mechanism. EMI from source to victim can couple through inductive coupling or common wire coupling or capacitive coupling or radiative coupling. So these are the four ways of coupling. So we need to address in each and every aspect. Now, if you consider only inductive coupling, I have taken care, sir. I didn't concentrate on remaining thing. We cannot expect from which mode it will couple the source. The coupling path can be which mode we cannot assume. So for example, you have taken care everything. Your box of the complete product is, you made it as a box, metal box. So one more product is come through nearby. So that product box and your box is close proximity. Then capacitance effect will come between these two. So that has to be taken care in design of each and every aspect of your design. So what is, as of now, we have seen EMI, what are the sources of EMI, all these things. Now what is EMC? So EMC is your ability of your system or a product or your equipment utilizes the electromagnetic spectrum while its operation and while performing its intended operation without suffering unacceptable degradation or causing unintentional degradation because of electromagnetic radiation. That means your product should be satisfactorily work in electromagnetic environment. Satisfactorily means what? Acceptable degradation. Without degradation means, okay, how much acceptable your degradation. Sometimes 230 volts, you can accept up to 220 volts because our 220 volts also my equipment will operate. So that is acceptable degradation. Similarly, unintentional degradation. Unintentional means, intentional degradation means it is intentionally happening. Unintentional degradation, how much degradation you can accept. So that has to be also into your satisfactory performance. So that can be made our defense or industrial electronic systems, either defense or civilian sector electronic equipments, made compatible with each and every environment such that our electronic systems will not disturb electromagnetically. So how EMI is coupling? It can be coupled through conducted mode or radiated mode. When it is conducted mode is coupling, it can be two ways. It can come from the equipment as emissions. It can be given onto the equipment to check the immunity. Immunity is called susceptibility. So we can check the immunity of the equipment. Similarly, radiated emissions, radiated way it is coming from the equipment, and radiated way we are giving onto the equipment. That means we are giving some disturbance signal. We estimate some of the signals. For example, if you take lightning comes. So due to lightning, this type of environment can be created. We can check in the laboratories. We will give indirect lightning effect. Like lightning, it can come when it is happening. Our cable is exposed to the lightning. How much current can be coupled onto our cable? That environment we will estimate and we will give onto the equipment power cable. This much current is inducing. When this much current is inducing this much characteristics of the waveform, then it will indicate the actual lightning waveform. So that has to be created. Injected way we can eliminate. So we have to check the performance of the equipment in 4 categories. We have to estimate in conducted and radiated mode, and we have to give the immunity of the equipment, susceptibility of the equipment for both radiated way and conducted way. So how the EMI measurements will takes place, where the antennas will be used in EMI measurements, I will cover in the next coming slides. So this is the very important. Decibel is a used in electromagnetics to express very big and very small numbers. For example, 0.001 10 to the power minus 5. That means 1 lakh times down from the 1. So then how to like express? If you write numbers, one decimal if you forget, then it will be vary the it is not easy to express and easy to multiply calculations. So we need to consider very big number and very small numbers, and kilovolts and megavolts can be expressed in dBs, and microvolts and picovolts and picoteslas. Like that also we can express in dBs, such that adding and subtraction will be easy and easy to visualize the EMIMC measurement terms. So this is named after the Graham Bell. So power means 10 log and voltage means 20 log. So that will be explained in the next slides. So these are the measurement instruments we are using in EMMC laboratories, in every EMMC laboratory. One is anechoic chamber is required, and various measurement instruments, reamer, receivers, spectrum analyzer, signal generator for immunity testing, and antennas, various antennas like wire antennas, aperture antennas, all these things will be used. And these antennas are broadband antennas, not narrowband antennas. If you take any patch antenna or any normal antenna, they can be narrowband antenna. When it is narrowband antenna, that antenna will give high gain. When you are going for broadband antenna, because I need to estimate EMI signature not at specular band from that 0 frequency to, that means 10 Hz, 20 Hz, 30 Hz to complete 40 GHz range. So when I need to cover complete frequency range, so I need to be taken care of broadband antennas. So these are the various test locations. So whenever there is no advanced technology of anechoic chamber with absorbers, earlier it is there, they have done measurements in open area test site, OATS. There we can go very free, electromagnetic free zone area. Then we can go there and we can estimate. Our equipment can be placed inside. This is a shielded tent or some room. From there, with the antenna, we can estimate the EMI signature of a product. So when the technologies are developed towards metallic walls and shielded chambers and shielded anechoic chambers, now reverberation chambers, so TM cell, GTM cells, as advancements are going on, various measurement sites are coming, measurement locations are coming. This is called test site. The site where we can perform the electromagnetic interference measurements, that is called test site. So anechoic chamber also one test site. So various things will have advantage, disadvantage, that is separate subject. So shielded chambers, open area test is the ideal, but as our technologies are going on, our communications are going on, and that is difficult to identify the free zone area. Then it is moved to the shielded chambers. When you are using shielded chambers, again reflections are coming from the metal walls. So then replace with anechoic chamber, no echoes. Then no echoes from the walls and sides. So anechoic chamber is one of the advanced technology they are using. Still, full anechoic chambers are there, and reverberation chambers. Anechoic chamber is again not covering the all modes of electromagnetic disturbances. So reverberation chamber is one of the things they can cover various modes also, like coupling of various modes. And TM cell and GTM cells are very smaller versions of the anechoic chambers. They can use it for very portable equipment testings like mobiles, all these things. Circuit level things we can able to estimate EMS signatures, and also estimate the immunity of the circuits developed for low, like smaller circuits. We can use TM cell and GTM cells. EMC antennas. So what is an antenna? We know it is simply a device convert time varying voltages into the time varying radiated to electromagnetic field. So we are giving voltage and it is converting to the electromagnetic signal. So field generators such as TM cells, GTM cells, any parallel plates and triplates, strictly not an antennas. Antenna should be other side open. It has to be radiated onto the space. If you go here, it is a TM cell. This TM cell is not a antenna. If you are giving signal here, and it is propagating from with respect to the center septum to the ground. The field between these two is as like capacitor principle. One is highly positive charge, one is zero potentially charge. Between these two, electric field is existing. So electric field we are creating between these two plates while traveling the voltage. So that is field generators. So antenna is not field generator. It has to be radiate the electromagnetic energy through the space. So EMC antennas normally used for emission measurement and immunity measurement and shielding effectiveness measurement. For example, if you're developing any shielded materials. So for that qualification purpose, antennas are using, and site qualification testing. What are the sites I have mentioned earlier, like open area test site or anechoic chambers or shielded chambers. So these sites, EMC sites can be estimated using antennas, EMMC antennas. So these are the various terms of antennas. It's respect to the EMC only. I'm not covering all the antenna radiation parameters. So these are the parameters are very, very important with respect to the EMC, because our EMMC antennas are broadband antennas. So next, what is gain? Gain is inherently as a directivity. So gain and directivity have some relation. So directivity means it is a ability of antenna to concentrate a transmitted signal in a particular direction. If you observe here, the instead of radiating in all the directions 360 degrees, one direction it is increasing. That means particular direction, how much concentrately my antenna can radiate more. So that means taking the other side's energy and making in particular direction. So if a directivity is more, I can give very low signal, weak signal, I can generate radiated field as much as possible. How this passive antenna, this is a passive antenna because it is not having any active elements in this antenna. Passive antenna cannot amplify signal, but directivity is defined by comparing a theoretical omnidirectional antenna with respect to the same input power. For example, you are given a same input power ideal antenna, isotropic antenna, it will come some radiation in all the directions 360 degrees as a dBi. That means dB. So when same input power you are giving to your antenna, not omnidirectional antenna, your developed antenna. So when that changed the particular structure of your antenna, the radiation is coming like this. Instead of going in 360 degrees, it is coming in particular direction. So when giving same input to the isotropic antenna, you are giving this much. When giving same input to your antenna as a directional antenna, it is coming this much. So as compared to this antenna, the directivity is increased. That means you are not amplifying. It is simply converting other side energy into your particular direction by altering your structure, by modifying your structure. So it is not an amplifier. In some cases, gain is interchangeable with the directivity. Sometimes gain also includes the mismatch factor between the antenna and its feed. So if antenna and feed it is mismatched, then it will affect the gain also. So it is simply a bulb, light bulb compared to the flashlight. So normal light bulb will gives the light in all the directions. If you give a flashlight, particular concentration or particular direction only, intensity will be more. So flashlight is the directional antenna. Normal bulb is the isotropic antenna. Type examples. VSWR, reflection coefficient and return loss. These three are interlinked with similar phenomena. That means how perfectly matched your antenna to your measurement equipment. If perfectly matching means there is no reflections from the between these two, then perfectly matched, whatever the signal is coming in receiving mode, it will go to the measurement equipment. Similarly, whatever the signal coming from the amplifier, it will takes up and radiate into the space. So the matching is required perfect, otherwise some of the energy will get back. So for analogy point of view, flow of water through a pipe with unequal diameters, it will create it will go to the through pipe, some will be the reflected back. So if VSWR is 1, that means 1:1. That means perfectly matches, everything goes through the cable and matches to the radiated into the space. Then reflection coefficient is 0 and retinal loss is infinity. That means if VSWR is 2, for example, 2:1, 2, then 1/3 of the power is loss, like the reflection coefficient is 1/3 and 9.5 dB is loss. That means Out of the 100% of power, 11% of power is reflected. That means 89% of power only it is going to the load. Load or measurement equipment or to the antenna. So that means if VSWR is not properly there, so it is not properly matched, then it is waste of power in your handling. Then more power is required to get the particular desired power, and sometimes reflected power again disturbs our feeding equipment. So these are all things will be taken care. And antenna factor. So one antenna factor, it is in the receiving mode. It is completely in receiving mode. So you have a receiving antenna. Input for the receiving antenna is electric field and output will be the voltage. So normally electric field is equal to how much ratio between electric field to voltage. The conversion factor from electric field to voltage is introduced by this antenna. So that factor is called antenna factor. The ratio between electric field to voltage in a 50 ohm system is called antenna factor. The factor introduced by antenna while measurement how much electromagnetic disturbance present at its input of the, that means interface of your antenna structure to output terminal, that is how much voltage terminal is developed. The while conversion, some factor is introduced by this antenna. That factor is very, very important in EMI measurements because some losses are introduced by some of the things introduced by the antenna. So that has to be added. So that has to be added means that has to be characterized before measurement. So that antenna factor is again depends on frequency and gain. So if gain of the antenna is more, then antenna factor will be the minus, less, and frequency increases, antenna factor also increases. It is linearly proportional. Low frequency signals is antenna factor is less, and high frequency signals antenna factor is more. And antenna radiation pattern, beam width, these are all various parameters as similar to the normal antennas only. And polarization. And polarization point of view, in EMMC point of view, only linearly polarized antennas only will use, not remaining polarizations, because linearly polarization means it can easily estimate particular things like dipoles, bicones. These are antennas, linearly polarized antennas only will use. Remaining applications, electrical and circular polarizations are used. So bandwidth is the range of frequencies. So based on the bandwidth to gain relations, so gain bandwidth product is constant. And if you go larger bandwidth, gain again I need to compromise. And I want to concentrate on little gain, and bandwidth will be the problem. I need to restrict. So that purpose only we are keeping antenna bandwidth. And a balloon. So balloon is balancer line to unbalancer line transformed. It is a simply inductive transformer, balancer line to unbalanced line. Because if you take any antenna like dipole antenna, it is having one is upper arm lambda by 4 element and bottom lambda by 4 element. Complete together is lambda by 2. On top one and bottom one both are separated by particular distance and connected to a source. So that means two symmetrical elements. So that is balancer line. So that balancer line I need to connect to unbalanced line of coaxial cable. So how do I connect? So some of the things may not possible to provide proper transmission between these two, balanced to the unbalanced. So I need to use some balloons. So if you connect, it will provide low impedance for differential current. Differential current means it is going through positive and coming to the return only. Or common mode current means it is coming both the lines simultaneously. This means common mode current. So it has to be high impedance for the common mode current, that is noise, and it has to be provide low impedance for the your desired signal. So that is taken care by this balloon, and this can be connected unbalanced to the balanced line with respect to the ground. And unbalanced antennas have different responses depends on the which side is up when vertically polarized. So unbalanced antennas, for example, few unbalanced antennas are there that have some which side is up, everything we need to take care. So that will give some of the uncertainties in the measurements. So simply balloon is to connect unbalanced line to the balanced lines or balanced line to the unbalanced lines. So it is balloon. And near field and far field. Our EMMC measurements normally will perform in far field for commercial sector, but defense sector normally we will perform irrespective of the distance based on the defense environment. Because if you take any ship, all electronic systems are very within a 1 meter close proximity. So that means EMI disturbance one equipment to the other equipment within the 1 meter space distance. So we need to take care measurements in as close as possible in military sector. But in commercial sector, if you go, TV is there, from there 1 or 2 meters away from only we will be sitting, or some equipment is placing. So commercial sector, either 3 meter distance or 10 meter distance, we will perform the measurements. So near field and far field with respect to the based on wave impedance. So it is an impedance. So if it is a wave, impedance of a wave, what is the impedance of a wave? Wave, if we have electric field components and magnetic field components, the ratio between electric field component to magnetic field component, that means V by I, as like V correspond to the E, H correspond to the I, E by H will gives the Z impedance. So electric field wave, if you take E component and H component divided by both these two will gives the electric field impedance. The wave impedance is purely depends on source characteristics when it is very close. For example, you have a source very close to the source, then the wave impedance is completely depends on not by media. It is closely depends on your source characteristics. If source is electric field source, when electric field is created based on capacitance principle. So capacitor is voltage. So where voltage can be potential will be high, voltage when it will be the high, when load is infinity load only we can get the high voltage. And current when it will get high, when impedance is very low. That means short circuits only get infinity currents. When it is a short circuit corresponding to the high current, corresponding to the magnetic field, it will gives to the low impedance of the wave. If it is a source is electric field source, it is a voltage source, it will provides infinity impedance. When moving away from the source, from particular distance, electrical distance, when it is moving away from the source, slowly independent on the source characteristics, it is completely depends on the medium characteristics. Medium means what medium you have between your observation point to the source. That means if you assume as a free space, if it is a free space, it is completely depends on free space impedance 1 by root 1 by 2 by 1 by root of L by C, that LC, it will gives mu naught epsilon naught. Mu naught is some value, epsilon is some value of a air, it will gives some 120 pi impedance, the free space impedance. So when you move particular away from your source, it will give 377 ohms at particular distance. The distance before this is, we will estimate as a near field. Above this is, we can estimate as a far field. So we can perform these measurements based on this. And wave impedance is very, very important while measuring the some of the EMMC phenomena. So this again theoretical calculations like fractional region, near field, far field, some of the things they will use this equation, some of the things they will use this equation based on the various theoretical involvements. So these are the various terms we have covered, EMMC terms. Now typical EMMC antennas. So what are all the antennas are there? Typical EMMC antennas. So I will cover in detail. One is loop antenna. One is loop or magnetic coil. So if you take a loop, it is a very low frequency, because low frequency signals have depends on current. So current is going in a particular loop. When current is going on a particular loop, the magnetic field will be induced around the loop. So that magnetic field will generate, and if any magnetic lines are passing along the through the loop, current also produce reverse ways. It is a passive device. One can transmit the magnetic signals, one we can receive the magnetic fields. So here one equipment is there. From the equipment, very close proximity, the electromagnetic lines are coming from the product. From there, I am estimating the how much current is inducing. So that current correspondingly, I can again recalculate back based on introducing the correction factor. I will estimate the magnetic field. That means some magnetic field is radiated by the particular product at low frequencies from 20 Hz to 30 megahertz. So this magnetic field induces some current in my loop. This loop antenna is converts from current to magnetic field to current. So that current, how much is coming, I will estimate. Correction factor I will add to convert to magnetic field. that magnetic field, how much is coming, I will estimate based on the standard requirements. So for that purpose, loop antennas are we are using for measurement of the magnetic fields. So normally most are shielded loops with a gap to prevent a shorting turn. Otherwise, it will make short turn means it cannot be proper performance cannot be given. So rod antennas are monopole antenna. So these are the counterparts of loop antennas. Earlier loop antennas are used for magnetic field measurements. So this can be used for electric field measurements at that same frequency, low frequencies, some 30 Hz to 50 MHz. So amplifiers within the antenna sometimes necessary for smaller signals, because very low frequency signals, sensitivity point of view, sometimes the very weak low frequency signals are very weak to pick up by these antennas. So some pre-amplifiers are required or some amplifiers are required. So that amplifier will amplifies the signal strength by decreasing the noise floor. It may not amplify completely. It will only decrease the noise floor. That means pre-amplifies the signal before giving to my measurement equipment. Noise floor can be decreased and my signal strength will be shown as an increase. That means you have two lines. I cannot increase this line. I can decrease this line. That means it can show signal strength is more. So for that purpose only, these amplifiers are using pre-amplifiers. So dipoles are after this above 30 MHz, dipoles are using for various tuned dipoles, like various dipoles in based on the frequency of interest. So we will based on lambda by 2 lengths, we can estimate and we can use tuned dipoles. That means it is a one dipole, one tuned frequency, one dipole, one tuned frequency. So whenever these tuned dipoles are there, it will give accurate gain, accurate radiation resistance. It is ideal antenna. But in EMMC point of view, if you use this antenna, every time we need to check frequency by frequency, one dipole, one time measurement, one dipole, another type measurement. Measurements are more. So for this point of view, they have replaced it with advanced like antennas like biconical and LPD antennas, logarithmically, periodically dipole arrays. So they have placed periodical dipole arrays in logarithm manner. So that dipoles in array manner, and biconical antenna, it is a two cones. Cone is there means the bandwidth is increased. So for increasing the bandwidth, cones are using. So these two cones they are using for better matching of impedance. So high VSWR point of view, below 50 MHz they are not using. So above 50 MHz to 300 MHz these are using. So this biconical antenna will give better performance for the EMMC point of view. And logarithmical dipole array from above 200 to 300 MHz to 1 GHz. So earlier we have started with 20H loop antenna, wire antennas, then biconical antenna, then LPD antenna, logarithmically log periodical dipole arrays. And these antennas will cover normally gain about 5 dB gain will give. Then hybrid antennas, biconical, because one antenna, hybrid antenna can cover both the spectrums of the antennas. One is biconical antenna, other is LPD antenna. Both can combine together. I can cover from 20 mega to 30 mega or mostly 100 mega to 1 giga, 6 giga range. I can cover with simple antenna. That means I'm increasing the bandwidth. So definitely gain will come down, but bandwidth will increase such that I can able to perform the measurement. When my gain is not there, so I can utilize some of the amplifiers as an input. I can radiate through broadband antenna. This will decreases my number of measurement attempts by the antenna iterations. So antenna iterations, sir, I can made it as instead of 2, I made it as 1 now. So this is horn antennas. Ridge horn means it is broadband horn. This is standard gain horn means it will give standard gain, but it is not cover the full band. So these are the horn antennas. So as per the theory, we'll have horn antenna as like a simply coaxial cable. If you have a coaxial cable, if you separate a particular distance, it will give impedance expanding. Like instead of coaxial cable 50 ohm, then we are expanding. It will give impedance is changing between the center connector and shield. Then space is more. At particular distance, it will give 377 ohm. So at where 377 ohm is coming, there accordingly we need to check H plane and E plane type of antennas. and accordingly we need to give the feed and waveguide, and coaxial cable to waveguide transmission is very, very important, and waveguide to radiation point of view, we have to have as tapper section, this waveguide section, everything, and with advanced technology of ridges. With ridge means we can increase the bandwidth. So this is the feeding point where we need to give feed for the coaxial connection. So that as per the theory, we need to be taken care of our waveguide length, and based on the waveguide, like waveguide length, lambda by 4g from the source, we need to give the source point, and this height of this center conductor. That means coaxial cable center pin, how much height we need to keep it, such that the proper transmission between coaxial to the waveguide will taken place, and wave will be properly transmitted in the waveguide. From the waveguide, again tapering will takes place, and for radiating onto the space. And these are the various standard gain horn antennas. So wherever it is not possible covered with antenna of ridge antennas, so standard gain horns are not possible to create from 1 giga to 40 giga with single antenna, but ridge antenna can cover from 1G to 18G, 1 to 40G, like that we can cover. But in standard gain horn antennas are not possible to cover. So gain we can, if you want to get more, then bandwidth we can make it as a less, like 1.5 megahertz, like 1 giga to 1.5 giga, one antenna, 1.1 to 1.7. 1.7 to 2 giga. So 1 giga, 2 giga bandwidth, if you take, the gain of the antenna will be more, like 20 dB, 30 dB gain will you get it. So whenever somebody cannot afford for amplifier purchase, they can design this antenna, standard gain horn antennas, such that they can radiate more power. So these are the double ridge horn. That means one antenna is covering from 700 megahertz to 40 giga based on this ridge technology. So these are a very versatile and broad band, and they can cover from few to like few gigahertz range. But make sure that beam width meets your measurement requirements. Beam width means how much, like I cannot cover complete beam. So accordingly, I can concentrate on more points. For example, big equipment comes, antenna size is very small as frequency is increasing. Then I need to cover beam, like various equipments parts. I need to expose electromagnetic disturbance. Then I need to cover various points. And this is the emission measurement, how to estimate electromagnetic disturbance from a product. So this is a equipment. From this electromagnetic disturbance is coming, you assume I have a antenna, I have a cable, I have a preamplifier, I have a measurement equipment, measurement noise meter. Okay, first equipment, when I measured, from here electric field is there, here I am converting voltage. Electric field to voltage, when I am converting, I need to add antenna factor, because antenna is having some losses. When any loss is there, I need to estimate how much electromagnetic disturbance coming here. So whatever the display I am showing here, I need to estimate electromagnetic field available here. So I need to add antenna losses. Then cable while propagation, some losses is there. That loss also I need to add. Now A loss and B loss, both I need to add. Then preamplifier. That means amplifier, it will amplifies the gain. So that means originally it is not there. Original signal strength is not there. I am amplifying, that I need to remove. And second cable loss I need to add. So that means A, B and D I need to add, C I need to remove. After making all these corrections, I will get the actual result, how much is possible to estimated equipment output. So these are the measurement process. For that, antenna is required, various cables are required, preamplifiers are required for the emission measurement. So this way we will perform the measurement at EMMC laboratories. So where we will keep the equipment and anechoic chamber such that no electromagnetic disturbance coming from the outside environment, only we are estimating from the equipment. And we are estimating the equipment using different antennas. So different sectors of equipment will be estimate the electromagnetic disturbance, and we will perform as like explained in the previous block diagram. And similarly, immunity measurement. So now I am giving a signal onto the equipment. So that means here instead of field probe, yeah, you assume as a one equipment is there. On the equipment, I need to give the signal. So for giving the signal, I require signal generator. So signal generator, then amplifier. Amplifier amplifies the signal strength. So and forward power and reverse power and directional coupler is required, such that how much power is going to this, I need to monitor. That means how much signal it is going to the antenna, I need to monitor means I need to monitor how much power is going to the equipment. For that purpose, forward power and reverse power will be monitored. And also when any reflections comes, my this port will indicates how much reflected power coming also. That also I need to monitor. So first you have a signal this much level, that means minus 5 dBm signal you are giving at particular frequency. Then you have 47 dBm gain. That means minus 5 plus 47 dBm, it will give some 42 dB like that. Then you have an antenna having some transmit antenna factor loss, then it will be removed, and also have some particular distance. Then you will have particular level, how much you are getting here. For getting more signal, whether I need to increase antenna gain or I need to increase amplifier gain. So these two are very, very important in radiating immunity testing. But in emission measurements, always you have to take care of less losses. Here it is required more strength level. There it is more sensitivity, here more level it is required. So both we need to take care of. So that means if it is having antenna gain more, it can use the antenna for immunity measurement. Any antenna is used for low antenna factor, that can be used as a emission measurement. So same antenna cannot be used for both emission and immunity measurements. So this antenna is immunity measurement antenna. So we are giving signal onto the equipment while giving the signal from the signal generator, and it is radiating onto the equipment under the test, and equipment functionality will be monitored while measurement. So as of now, we have covered EMMC antennas and EMMC basics, all these things. So next I would like to go for various EMMC antenna simulations. So computational electromagnetics, it is having various softwares like HFSS, FICO, CST. So these are all will be markedly available softwares. They will provide various computational electromagnetic capabilities. So that will based on again differential models or integral models. Integral again time domain or frequency domain, time domain, and differential models again time domain, frequency domain. So based on your requirements, we can select suitable solver, suitable software such that you can simulate your requirements. So these are the various how to select a suitable numerical technique. So whether I need to go uniform theory of diffraction, or I need to go physical optics solver, or I need to go method of moments, or whether I need to go finite element method or finite difference time domain method. So are some of the hybrid solvers are required. So based on your complexity of the material, based on the electrical size of your equipment simulation, when you are going for simulation of ship, then you have to go for either physical optics or uniform theory of diffraction when complexity of the material is less. When you are going towards complexity of the material is more, metamaterials, various complexity of the material properties, then you have to go for finite element method or method of movements and finite difference time domain methods like that. So this selection of suitable material, suitable solver is very, very important in performing the electromagnetic simulation measurements. So some of the electromagnetic modeling examples, one is simple dipole antenna. This everybody knows our like many of the electromagnetic domain. So simply a dipole antenna, we can take it. This can be shown as example to the students, like simple dipole antenna 300 megahertz, like resonant wavelength 0.5 meters, length of the antenna is coming almost 0.5 lambda by 4, 0.25, 0.25. Then it is giving gain of 1.5 dB. So ideal dipole will give normally 1.5 dB. Monopole means around 0.7 dB like that. So this is the where it is radiating 300 megahertz, but it is coming 280.5, 285.5 because of that this feed, some gap is there, that is also coming into picture. When it is not considered practically, that will come down. And radiation pattern as expected in the dipole has a 8 symbol like dumbbell symbol, and maximum 90 degrees and 1.6 dB gain. And field is inside a metal sphere. If you take any sphere, metal sphere as like Faraday cage, no electromagnetic fields will be going into the inside. So here only I am giving electromagnetic signal outside, and I am estimating inside how much is going. That means if any Faraday cage if you take as a ball, and no electromagnetic field will go to the inside. and antenna coupling analysis on a particular defense sector. So you have a different antennas, one antenna here, one antenna here, another antenna here. So you have three antennas. You assume as a one is transmitter, other two are the receptors. So one is at fundamental frequency, second two are at harmonics of the fundamental frequency. So then coupling between these two antennas how taken place. Whether this antenna to this antenna coupling is mode or this antenna to this antenna coupling is mode, and we can optimize the antenna location on a particular structure, either ship or aircraft or helicopter, whatever structure. We can optimize the location of the antennas, and we can optimize its performance to minimize the antenna to antenna coupling. So antenna coupling analysis also we can able to carry out, and antenna to cable coupling. So you have an antenna and nearby one cable is there. So that cable to antenna, if antenna is radiate a signal, how much radiated electromagnetic signal will couple induce the current or voltage on a cable nearby that things. So that we estimation we can take how much, like you have a 10-meter tower antenna, it will operate at HF band 3 to 30 megahertz, and it gives input power of 10 watts. Then a nearby coaxial cable we are estimated as a minus 20 dBm, 20 dB coupling is there, 20 dB volts coupling is there. And similarly, open TEM cell, what I have explained in the earlier as a site for measurement of estimation of low portable devices like mobiles and small PCB circuits. eMMC signature can be estimated using this TEM cell. So this TEM cell is we can operate up to 1 gigahertz from low frequency. So we can estimate the equipment's EMI compatibility using this TEM cell. So transverse electromagnetic cell. So electric field, this transverse electromagnetic cell S parameters and resonance frequencies, and these are the various pulse analysis in a TM cell. So TM cell will radiates continuous signals. So we have analyzed for the pulsed fields also and transient fields. How response of a transient fields it is there in the double like TM cell we have estimated. So the TM cell for this is one of the electromagnetic pulse signal. This electromagnetic pulse analysis in TM cell also we have estimated for detecting the pulse signals in a TM cell for measurement of voltage like field sensors. So like transient field sensors, if you have, we can calibrate the transient field sensors using this TM cell. And expand horn, simple horn. This example is there in our Constante Balanis textbook. So X-band horn 8 to 12 gigahertz. The theory based on the theory, it is been simulated, and results are coming at par with the theory. 22.5 dB gain of particular bore side direction, and VSWR of less than 1.5, almost 1, from 8 to 12 gigahertz, like 8.5 to 12 gigahertz. Here it is coming more, that means below the X band. So that antenna cannot be used below the X band, it can be used at only X band. It is like standard gain horn. So gain is providing 22 gigahertz, 22 dB at particular band only, not complete band. And this is the X band horn VSWR return loss. So return loss based on the VSWR, again it is coming minus 25, minus 15, minus 20 return loss is very good. And microstrip patch, I would like to show the wire antennas. Aperture antenna is over now. Patch antenna, simple 2.4 GHz patch antenna, and it will have some patch and it will radiate in particular direction and particular gain, and the two resonance frequencies are coming patches. So iPod electromagnetics, and Samir is doing modeling activities, modeling assignments, simulations in various domain. One of the domain is hyper electromagnetics. We will radiate electromagnetic pulse transient signals for various wideband spectrum, because impulse signal only can cover infinity bandwidth. So impulse corresponds to the infinity bandwidth. So we are dealing with all the frequencies in single go by impulse signals. So we have some impulse radiating antennas. The pulse can be radiated by using impulse. So impulse radiating antenna will cover all the spectrum at single go. Real-time event we can create as like electromagnetic pulse or lightning type of events by using these antennas. So we are doing research in that domain, various interaction of electromagnetic transient pulses onto the equipments. And these are the various eMMC aspects in various antennas, development and modeling and analysis, and horn antennas, biconical antennas, various calibration jigs for metamaterials, all these things we are doing in the research. And EMC aspects in antennas miniaturization. So when you are going towards miniaturization, how the EMC aspects will need to be considered. So what is miniaturization? It is a reduction of size, overall size of your development, such that you can able to achieve required performance with minimized size. That means you are miniaturizing the complete structure. So when the initially transistors, then field effect transistors, then MOSFETs, when you are going technology more and more, so your size of the equipment will be come down, miniaturized, but you are not compromising the parameters of your requirement parameters. So when you are moving towards miniaturization, when you are decreasing the size, so how the when your different antenna modules are placed in a close proximity, then it is leading to the circuits EMI problems. So that has to be taken into consideration while miniaturization for EMMC point of view. That means the process of replicating an antenna and circuit functionalities while reducing its size can be termed as miniaturization of the antennas. That means various generations of the computers. Initially, it is their large computers in first generation, then second generation, third generation, fourth generation, fifth generation. Now we are getting small laptops, palm tops. So various circuits, when technology is very large scale technology is going on, like medium scale technology, very large scale technology, when you are moving towards miniaturization, like technologies of integrations are taking place, large scale integrations. So then EMIMC problems also will be expecting. So that has to be taken into consideration. So what are the challenges in miniaturization? First, as many of your professors are like already doing the research in this miniaturization, the reduction of the size is significant portability of the equipment, and single entity. Many antennas can be included working in a multiple frequency bands and wide spectrum for the device to work. So these are the various techniques of miniaturization, material you are concentrating, and various shapes of antennas you are changing such that it can cover various bands, like one band, and that duplicate band can be used for other application purpose. And some of the foldings and sortings also you are implementing. Some of the slots also you are implementing. Some of the defects in ground plane also you are taking care. And various technologies are there. So when these techniques you are using miniaturization, some of the techniques will leads to the coupling between one circuit to the other circuit, and you are taking openings more, automatically couplings will takes place. When you are defecting some particular ground you are defecting means EMMC point of view it will create some problem. So ideal ground means okay, it will swallow, but when you are defecting the ground for your application point of view, again EMMC point of view it will be has to be considered. So again, circuit level, PCB level, how EMC has to be addressed. So that we need to take care. So these are the techniques. One is we need to use EMI filters if possible. If you are designing electronic circuit for EMMC point of view, we can use EMI filter such that this filter will eliminate any noise coming through conductor path. And circuit partitioning. So such that you partitioning the circuits in such a way that group the various high frequency signals are one location, low frequency signals are one location, pulsed signals are one location, and like that you have to partitioning has to be taken care in your circuit level such that EMI problem can be minimized. And grounding also has to be properly implemented. Various grounds, circuit grounds, system ground, analog ground, digital ground, and ground phenomena, ground philosophy, everything, ground planes, everything we have to taken care. And screened enclosure, some of the circuits, some of the components, wherever it is possible, you try to implement with shielded gasket if it is any possible, but you have to taken care of its heat also. Heat also has to be taken care. Otherwise, if you close completely, heat will be melt the component, and again components will be leads to the burning. So that has to be taken care. And screened lines and cables, wherever some of the cables you are using, try to use shielded cables or some of the screens on the particular raw wire. That has to be taken care. So these are the various design considerations. First one is internal processor as like digital clocks it can be taken care, and power lines, interface cables can be properly handled, and openings and ventilations of the walls of the equipment case has to be properly made. So that means the openings and ventilations you can keep it other side. If you have any source of this side, then you keep it other side. And signal layouts and mixed PCB groundings as properly maintained, and IO cabling properly handling, everything you have to be taken care. So this is the EMI filter. So how the EMI filter will works? You have a power, you are coming from other side. So power it is coming, this inductor will attenuate the low frequency signals, this capacitor will attenuate the high frequency signal. So simple inductor and capacitor circuit only, simple passive network, it will not create any harmonics and interharmonics, only eliminates the electromagnetic noise coming from the conducted path from other equipment to this equipment. So this is as like filter, it will eliminate the differential noise and conducted noise when it is designed for both applications. And circuit partitioning. So if you observe in this, Wi-Fi, Bluetooth, and GPS, cellular. So these are all antennas. So antenna related RF ports, you keep it one side. Otherwise, if you keep it one RF component here, one RF component this corner, one RF component this corner, then all are disturbance. And digital circuit, all digital parts are keep it at one location, and all motor controls you keep it in one location, and power supply you keep it in one location. And if you keep it analog and digital separate, it's better. So in such a way that keep analog sections away from the motor controls. So always analog sections keep the motors. Motors is the noisy components, it will create the noise. So it will easily couple the analog circuit, because analogs are noisy components. Again, even small noise also it will signal to noise ratio is less. So noise it will easily coupled into the analog. But digital we can eliminate based on the various coding techniques, various robotness codings. We can eliminate it as digital, but in analog we cannot eliminate it. And keep the power conversions and motor controls near power entry point. Wherever power coming, there only you can keep your motors and power circuits. And all power and IO should be filtered and transient protected. Any transients are coming, you keep it as a transient protected. So these are all taken care. And non-critical EMMC areas also you can keep it in the grouping. So this partitioning of the various circuit elements, circuit components, you have to be taken care at each and every board of your development in product development. And design techniques of grounding. So for example, if you have a ground here and ground wire from here to here, if you keep more, then loop area from positive to this circuit will be more. If ground wire is keeping very close to your very small wire or very close to your circuit, then loop area is come down. If it is a larger loop area, that means you are allowing to circuit to travel more distance, more area, then it will EMIMC problem will be the more. Then if you are allowing smaller area, then EMIMC problem will be the less. Radiated electromagnetic disturbance will be the less, because loop is conductive wire. The conductive wire is low impedance path. So low impedance path here giving more area, then electromagnetic signal creating along this loop area is more. So length must be kept in a minimum as possible to minimize your EMMC problems by induction. And some of the techniques to use screened rooms, screened enclosures, like some of the shielded materials, such that no electromagnetic signal from inside to outside, outside to inside. So this has to be taken care while designing. And some of the shielded cables or some of the immunity cables are like some may be perfectly shielded cables, some may be small shielded cables. So that shield, braided type shield is very good as compared to the complete conductive type, such that it will give inductance to capacitance relations can be minimized. If you take complete wire and length of the wire if increases, inductance will dominate. L is directly proportional to the L. Like inductance is directly proportional to the length of the element, length of the wire. If you have a braided element, then the gaps between this wire path to wire path, capacitance will come into picture. So L and capacitor will different signatures. One increases, other will decreases. The always will maintain the proper impedance. So braid is always very, very important as compared to the continuous conductive material. So as of now, I have covered EMMC antennas, how the antennas is using various antennas, EMMC measurement terms, antenna measurements, and antennas, what are the things we will use, and antennas in miniaturization, EMMC aspects, as we are large scale industries like technologies, VLSI integration technology leads to the miniaturization of the antennas towards 5G, 6G. It will give some of the EMMC problems, how to those problems can be analyzed. I have covered. Then I would like to show finally few facilities of our Samir. So these are the various facilities. One is highly specialized electromagnetic pulse system for larger objects and pulsed current injection test system as per military standard 188-125-125-1 and 2, and ultra wideband system. That means I am covering complete band up to far to few frequencies to few gigahertz in single pulse. Ultra wideband signal using impulse radiating antenna, and defense military EMMC test facility as per latest military stand 461G that includes lighting and electrostatic discharge, and EMMC modeling and computational laboratory, and on-site electromagnetic lab such that wherever any electronic equipment defense system not possible to bring our any EMMC facility, we can go there and we can estimate the as a doctor. We can go there, we can estimate the EMMC problems. So that means instead of bringing the equipment to the laboratory, we can go there and we can estimate. So there, what are the challenges? What are the limitations will be the again subject, different subjects. So now EMP. If any electromagnetic pulse generated by either naturally or intentionally, so the EMI will be coupled through wire front end. Front end means wire and back end means unintentional paths like conducted wires or some of the openings, some of the back end couplings. So one is front end coupling, one other is back end coupling. Front end coupling means you are doing some communication from your equipment to the outside through your RF channel. You have a RF equipment, antenna equipment. So you are intendedly doing some communication or internally you are receiving some signal. So that is always required for your operation of your equipment. So that means you are already opened for that signals coming in that direction. So that is RF front end. You are frontly opened for that particular purpose. And back end means your other wires, power wires, communication wires, control wires, and openings, windows, doors, all these things. So you have a facility. For example, if you take a house is our door is front end. If your door opens only, human personally in and out can be happen. And windows, some of the cables coming from DTH cable, power cable, and telephone cable, and wireless communications, each and everything you are coming through back end coupling. So back end coupling and front end coupling both has to be taken care while treatment. So this is our electromagnetic pulse test facility. So this is one of the India's largest facilities having a capable to test equipments of size 18-meter length and 12-meter width and 3-meter height. As like trucks and military systems, we can able to test for electromagnetic pulse. So pulse is generated by nuclear detonation. So the same incident we are creating here. So from here we have some 1000 kilovolts. That means 1 megavolts transient generator. So from that I can give transient signal and it can radiate, transmit, and it will create the electromagnetic pulse here. And I will bring the equipment here. I will keep here and I will radiate electromagnetic pulse and I will check the functionality of the electromagnetic pulse, its functionality. This is one of the India's largest as of now, as per Ministry Standard 461. Here is the verification, like testing, how we are doing. I will keep the equipments on equipment testing zone area. From control room, I can generate transient electromagnetic pulse and I will check the functionality of the equipment. When this electromagnetic pulse is radiated, an incident on a particular facility, which is shielded facility already, and some of the entries, like cable entries, are possible to pick up some current due to this incident and go to the inside. So that current is called pulsed current. So earlier I have checked for radiated fields. Now I will estimate this currents, how much is going through this conducted path. So that estimation we will carry out based on this pulsed current injection test facility. We will inject some of the currents which is due to electromagnetic pulse. So that current functionalities we will, when current is coming, the protection methodology used here while entry, they will use some protection methodology. That means filters, HEMP filters, EMP filters, they will use to eliminate the outside electromagnetic pulse coupled through conducted wire. So that will be evaluated against this type of pulses. This is the first of its kind in the country. We are doing any nuclear detonation takes place through conducted path, how much electromagnetic disturbance is coming into inside, we are estimating and we are evaluating as per the standard requirements for the strategic applications. So these are the various pulses, very short duration pulses of nanosecond range. That means nanosecond means correspondingly gigahertz bandwidth will cover, and 5 kiloamperes of current we are giving of transient pulse. So these are very, very important for various equipments used in the defense critical time urgent command control computer intelligence operations are doing in a particular defense mission purpose. So that missions has to undergo this type of evolution treatments. So this is the facility how we will test. Like here at the entry of your facility, you have some protective device. That device, how protectively it is protecting against the electromagnetic pulsed current, we will estimate while terminating the matched load. So that we are evaluating in the EMMC laboratory. So here, this is the Ethernet connector, Ethernet filter. So that means data, Ethernet data or your internet data from outside to inside is required for our command computer intelligence operation purpose. So when that is coming, you assume as this is outside exposed to the natural electromagnetic pulse. When exposed to this, some current is induced on this, that current should not go to inside. That means this device will provide some attenuation. So that attenuation is properly providing or not, we are evaluating here. And this is the impulse radiating antenna. We are used, it is available here for radiating the electromagnetic pulses of very fast electromagnetic pulses of picosecond range duration corresponding to the 100 tens of gigahertz. And it will be used for localized EMMC testing, and we can able to generate intentionally. I can generate electromagnetic signal onto the particular structure. I can disrupt the operation of the equipment. But I'm estimating the structures of the equipment, like electromagnetic disturbance on a particular structures. I can estimate on site also. I can carry this equipment to the site. I can estimate the electromagnetic disturbance. I can check the immunity of the equipment for transient electromagnetic pulses. So this way I will carry out various measurements. So like on building, I will radiate the electromagnetic pulses, how much is coupling inside the building with various protective methodologies I am estimating. And similarly, we have anechoic chamber of 20-meter length, 22-meter and 16-meter and 10-meter with dimensions. It can able to allow 40 tons load equipments into inside, and it will operate 40 up to 40 gigahertz. Can able to generate electric field strengths of 200 volts per meter, and it is capable to do all military, commercial, and automotive and avionic equipments. So all four sectors of equipments can be able to estimate EMMC analysis, and we can provide the solution. Like we have design experts, like EMMC design point of view, we can suggest them for EMMC qualification. And whenever any equipment is not possible to bring our factory, our test facility, we can go there. Few equipments are very big equipments like alternators, turbines, very, very big equipments like panels for fixed locations. It can be above ground or below ground. So any particular locations, it cannot possible to bring to our location. We can go there, we can assess the immunity, or we can estimate the electromagnetic signatures at site factory itself. And these are the various modeling tools we have at our EMMC laboratory, our VISAC, and ultra hyperworks FICO simulation tools, CST and HFSS. And as I've explained, we are doing various modeling assignments, and we will do in electromagnetic environmental effects, E3 domain. There it will cover hyperelectromagnetics, antenna designs, EMMC, PCB designs, coaxial cable analysis, antenna couplings, antenna mapping, RF mapping. Each and every sector will cover. We are doing research in 3D electromagnetic simulations. So thank you. If any questions, I will happy to answer. Please let me know if any questions have from any of the participants. So with this, I'm concluding my presentation on EMMC antennas and its antennas challenges in miniaturization.
Dear participants, if you have any doubts, you can ask to sir.
Hello, sir.
Yes, madam.
Sir, can you explain the fourth example from antenna to antenna interference and a flight mode you had shown, sir?
Yes.
That means generally we are expecting receivers or transmitters for the outside or inside environment. Here you are telling receiver and transmitter kept on the same environment. What is the need of having two receivers in front end, back end, one transmitter?
This one only, no?
Sir?
Now it is showing this one only.
We are not able to see your PPT, sir.
So
Fourth example.
sharing is not there, sir.
Yes,
Sir,
sir.
I have just shared, sir.
Four.
I have just make you host, sir. You can share.
I have to share again.
Ah, yes, sir. You can share again, sir.
Check, madam, it is coming.
No, sir.
Sorry.
Now it is coming, sir.
Now it is displaying.
In this case, generally we are expecting transmitting to outside, receiving from outside, but here you are telling the back end is going to be transmitter, these two are going to be receivers.
No. For example, you have on particular ship or aircraft, helicopter environment, you have both transmitters and receivers. Am I correct?
Yes, sir.
For particular application purpose, you will transmit. Particular application purpose, you will receive.
Okay.
Sometimes both same can be as a trans receiver.
Yes, sir.
So, for example, you assume as this is transmitting at HF range. For example, if you assume as a 15 megahertz, it is transmitting. So you are receiving another receiver at 30 megahertz on same HF range for particular application.
Okay.
So this while transmitting second harmonic is 30 megahertz again. So because of this fundamental second harmonic, how much you are receiving at your receiver itself? That means if you receive second harmonic into this second receiver, nearby receiver, you misunderstand that instead of getting original signal, you are receiving from your own transmitter itself.
Okay.
So that means antenna to antenna coupling can minimize. The estimation can be coupling can be minimized based on this analysis.
Okay. So can you able to, sir, your session completed or not? I don't know. Can you able to give some simulation results we are expecting, sir? This theoretical analysis everywhere we are getting, but we are expecting at least one simulation, one application in a particular area. If we are telling in aircrafts and ships, like that we are expecting in all conference.
So these are all things we are doing, madam, but only simulation means again I need to give software again I need to run and again need to show the results. That will take again.
That's what we are expecting from the experts, sir. Everywhere we are getting theoretical results. What they got, they are showing, but we don't want what they got. At least some push up for the learners interested in a research area. We are not getting anywhere, sir. Self-learning means it takes lot of time. Maybe we are striking some other points. We are not getting.
Okay.
That we are expecting, sir. Theoretical analysis, okay. Some conference papers.
No. What are all the simulations we have shown here? Not all simulations what we have carried out. Few simulations which are easily understandable by the educational learners. I have shown here. These are all things done by us only. What are all things we have done?
But we are expecting a little bit push up
Okay.
In terms of real-time results, all
Okay.
these are we are getting theoretically. If possible
Okay.
for you, we are
Okay.
expecting some simulations either in HFSS or CST.
Okay. Next time, if anything confident, like they will
Particularly,
arrange, we can like a modeling point of view, we can make it in that thing. Otherwise, we have a dedicated modeling lab. We can educate, but based on proper permissions, all these things are required.
okay, sir, basic level. It's not we are expecting research oriented. At least for our students, can we give us
But that point of it is available in the literature, man. YouTube videos is available. Some of the suppliers of CST, HFSS, FIC also they will provide do it yourself examples, so that you can practice while trial versions or your student versions. They will give some examples that step by step, your laboratory manuals are there, no? How to connect this
we are
component.
spending almost 3 hours per day. That means we are expecting that level.
Okay, okay, okay.
Okay, sir. Thank you, sir.
Thank you.
Dear
Thanks.
Any other questions, please?
Sir,
Yes.
sir, is there any testing of outside antenna, sir, in Samir?
Antennas.
Yes, sir. Antenna testing.
We don't have any antenna test facility, because antenna testing means again we need to estimate the antenna characteristics. Like for example, antenna gain, antenna radiation distance, antenna VSWR. Few things are possible, not all things. Like VSWR and gain we can estimate here, but we are not open up for the outside for the antenna. VMMC purpose only, but our Kolkata center will do antenna, all antenna parameters estimation, including your gain, polarization, each and everything. Like each 360 degrees radiation pattern also they will give.
Okay, sir. Sir, in one of the slide you are showing the structure of a mobile, right? Can you
That
go
is
to the slide?
miniaturization, no? Miniaturization, no?
So all the digital components one side, all the cellular component one side, and middle there is a analog.
This one?
No, sir. No, sir.
This one?
Yes, sir. This one, sir.
Okay.
Sir, if you provide the shielding in the cellular side,
Okay.
is there any chance to block the electromagnetic waves?
But if you give cellular side such that you have to
That means,
allow your signals to transmit, because that antennas are because these RF components are there here, it has to be allow the your internet signals. For example, you have a patch antenna inside,
yes, sir.
so that patch antenna should be open for Bluetooth and Wi-Fi communication. It cannot close. Only thing, your circuits which are used for driving the antenna, that can be you can shield.
Okay, sir. Sir, is there any frequency-wise difference between the computational models
Yes.
like FTDD?
It is there frequency wise.
Well,
Like for example, if you take one mobile, okay, if you model at megahertz, so that mesh size will be less, like moderate. If you go to gigahertz range modeling, then the mesh size will based on the electrical wavelength, it will be more cells will come, and your complexity of the problem will increase, and memory of the simulation also required more.
Okay. Thank you, sir.
Okay.
Good evening, sir.
Good evening, sir.
I have a question. If suppose some systems are frequency hopped system, that means they are working in a different frequency band. How
Okay,
to
sir.
measure the EMC for this kind of system, sir?
So that frequency, it will radiating or receiving, sir?
It is radiating. Suppose if some military jammers are there or some
Okay.
enemies, they may use frequency hopping to create some noises in particular frequency band.
So
But they
that
are
means
operating at different
those are called
frequency.
intentional transmitters, sir.
Yeah.
So that intentional transmitters at fundamental, definitely it will transmit.
Okay.
At harmonic, second and third harmonic, up to 40th harmonic, how it is restricting, we need to estimate.
Okay. But if that is frequency hopping means it will transmit in kilohertz, then
Band,
megahertz, then
particular
gigahertz,
band.
then in particular band.
So that band relaxation will be given because one particular percentage of bandwidth. Like for example, you are radiating for particular range, range 5% here and that side we can omit. It can possible to radiate. That cannot be estimated. That is intentionally radiate. That can be avoided. Remaining frequency range. For example, you are operating at 900 megahertz. For example, as a mobile purpose. Then you have to other band above beyond your mobile bands up to 40 gigahertz should not radiate any signals.
Okay. Sir.
Because you are using some of the transmitter circuits. You are taking signal and mixing some of the non-linear components, it will radiate some harmonics. So how suppressing your harmonics has to be one of the criteria.
Okay, sir. Okay. Again, I have a question, sir. In 6G, some are saying that it is affecting human tissues and human brain cells and all that. So what is actually the means practical, because you are working on it. So whether 6G affect human cells or not?
So that is separate domain, sir. They are doing research. So it is not completely proven. So we cannot comment on that. So as it is, technology is not fully operational. It is going on under research. Samir also part of in that 6G testbed development along with IITs. So that is separate domain. So still the operational, we cannot estimate its effect. It has to be
sir.
fully operational. Then only we can able to estimate.
Okay, sir. Thank you.
Okay. Sir, can we close?
Yes, sir.
Yes,
Yes, sir. Thank you so much, sir.
Thank you, sir.
Valuable information given to participants, sir.
Okay.
Sir, thank you very much. Sir.
Thank you, sir.
If
Thank you,
any
sir.
questions are there, anybody participants, they can share through my mobile number or whatever it is, mail.
Sure, sir. Sure,
And,
sir.
happy
Sir,
to answer.
sir, please share your PPT, sir.
Okay.
PPT is possible.
I will see, sir. I need to
Okay,
take some of the things, approvals.
Okay, sir. Okay, sir.
General information, whatever it can possible to share, I will share.
Sure, sir. Thank you, sir. Thank you so much,
Okay.
sir.
Okay. Thank you.
Good night. Good night,
Good
sir.
night.
Thank you, sir.
Okay.
Thank you. Dear participants, now one more session is going to be start within few minutes. That is given by Mr. G. Sambasiva garu, scientist from Hyderabad. He will be joined in this session, in the next session, within few minutes. Stay online. Thank you.
Sir, Sambasiva, sir. Sambasiva, sir.
Hello, sir.
Sir, will you start, sir? Yes, sir.
Yeah.
Yes, sir. Will you start,
I'm
sir?
ready, sir.
Okay.
Yes, sir.
Okay, sir. Okay, sir. Okay, sir.
Suresh
sir, please introduce, sir.
Okay, sir. My name is G. Suresh Kumar. I am working as assistant professor in Vignan Institute of Engineering for Women. Now I am going to give brief about our new speaker, Mr. G. Sambasiva garu. Just
Sorry, I'm K. Actually, surname mistakenly you have written K. Sambasiva.
okay, sir. Okay, sir. A little brief about K. Sambasiva garu. K. Sambasiva sir received his BTech degree in Electronics and Communication Engineering in 2003 from NIT Warangal, India. He received ME degree in Microwave and Radar Engineering from Usmania University, Hyderabad, India. Presently, he is pursuing PhD from IIT Tirupati. He was a technical officer in ECIL Hyderabad from May 2005 to June 2009. He joined Research Center Emirat DRDO Hyderabad in June 2009 and presently working as scientist in radar antennas and components division. He is senior member of IEEE Antennas and Propagation Society and Microwave Theory and Techniques Societies. His area of interest is microwave antenna and areas of radar communication and military applications. metamaterial-based antennas. He has published 15 research papers in international conference journals proceedings. He is also reviewer of national and international conferences. He has won the Best Session Paper Awards in ATMS 2016 Hyderabad and TRE 2016 in NIT Warangal. He has won Best Poster and Best Session Awards in IAIM IEEE Bangalore in 2017. He is a team member of DRDO Performance Excellency Award 2016, New Delhi. He has delivered oration on the occasion of National Technology Day and received Titanium Medal from Director RCA DRDO in 2017. Thank you, sir. Everyone, participants, good evening, everyone. Now, today, K. Sambasiva garu is going to brief about metamaterial antennas. Thank you, sir.
Yeah. Can I get the permission to share the screen?
Yes, sir. Yes, sir.
Yes, sir.
Just a minute. Sir, now you are the host, sir. You can share your PPT, sir.
Is it visible?
Sir, it is visible, sir.
Good.
Yes, sir. Yes, sir.
No problem. No?
No problem.
1 minute. Yeah. Yeah. Good evening, everyone. Audible?
Yes, sir. Audible, sir.
Yeah. Okay. So, thank you very much, Vignan University, for giving me this opportunity to share my knowledge. Today, my topic is the metamaterial for aerospace antennas. I am Sambasiva scientist from RCA DRDO. So, this is my outline of presentation. I'll be discussing about the metamaterial, what is exactly metamaterial means, and the principles of metamaterial and basics of metamaterial, and for various boundary conditions like PEC, PMC, and RIS, perfect electric conductor, perfect magnetic conductor, and reactive impedance surface. Metamaterial antennas, few of the antennas I will be discussing, and the applications of metamaterial antennas for aerospace. Some of the examples we will be discussing and references. So, if you see the metamaterial, basically they are the engineered structure. So it is not any different material. Actually, it is the normal material of a copper flat sheet, we can say. So, but by providing some engineering value addition to it, we are getting some properties like which are not available in nature. Okay, so that is basically, that means we are getting the properties which are not available in physical world by modifying the structures. Okay, PCB. So that is basically metamaterial. If you see the material properties here in this both positive, epsilon is the x-axis and mu is y-axis, both positive media, if epsilon is greater than 0 and mu also greater than 0, then refractive index will become positive, that we are generally calling as a double positive material. Okay, so this is conventional material which we are all the time we are seeing till now. But whenever any one of these epsilon or mu are negative, then this refractive index will become imaginary. So that means what? Refractive index negative means that impedance of that surface will become reactive in nature. That means field is storing in nature. So wave propagation further, it is not possible to extend its journey. Okay, so that way he will stop. So in the quadrant 2 and 4, wave propagation is not possible. That's why you see this wave is slowly, even rapidly dying down. So wave propagation further into this zone of material is not possible. And fourth also similar way. So how it is happening? Because of the epsilon negative, which is basically happening in the plasma set, that is particularly metals at optical frequencies, they will become evanescent. So evanescent means whose propagation is not possible. Okay. So, and similarly for the ferrites, also it is happening. Mu negative will be happening. So these kind of physical materials which are providing this band stop nature. So they are basically potential solutions for the observer application. Okay. So then coming to the fourth category where epsilon is negative and mu also negative, less than 0, both cases, then the refractive index will be negative actually. So what is the meaning? Refractive index negative means it will become left-handed system. So this both positive is a right-handed system, then it will be left-handed system. So, and backward propagation. So many features are there that we'll be discussing later. Okay. Design to perform extreme wavefront transformation. So we are modifying the amplitude and phase of the wave using the metamaterial so that we are getting extreme different features we are getting. Okay. It used to control the reflection and transmission of incoming plane wave. So in terms of the frequency as well as the angle of incidence. So we are able to control the transmission and reflection also we can control. So we all the time play with the materials. Okay. Homogenization could be achieved with the increase of density of unit cell. Suppose whenever wave is going from left to right, and this metamaterial unit cell, if the unit cell size is very much smaller, then energy will be penetrating through the metamaterial. Then homogenization means it is independent of the angle. That further I will explain actually. So basically, this metamaterial is a left-handed system. So it means it follows the left-handed screw rule. Normally, automatic wave will follow the right-hand screw rule. That when it's E plane, E vector and H vector, so E cross H will, this is the wave direction. So similarly, it follows this E and H. This way it will go. So that means left-handed system. And a double negative, because epsilon and mu both are negative here. And the negative refractive index and backward wave. So here what is backward wave? Actually, if you see the wave, there are two things, velocities. Okay. One is phase velocity and group velocity. So velocity with which the wave energy is propagating is called group velocity. The velocity with which the phase of the wave is propagating is called phase velocity. So both are same for the right-handed system. For the left-handed system, then phase velocity will be reverse actually. So whenever assume I am the source of a electromagnetic energy and going, so once the from the energy will originate from the source and going away from the source, right? That is generally happening. Even though if I am covered with the metamaterial shield, then still energy will go away from the source. That means energy propagation is continuous. It will not disturb. But phase velocity will be the reverse. It is coming towards me. So that way it is happening. That's why it's called backward wave. And the reversal of Snell's law. I will clearly explain each and every property with a slide. Okay. And boundary conditions also will be reversal. Negative phase velocity. If you see positive phase velocity, normal material or normal electromagnetic wave, when it is going away from the source, whose phase is reducing actually. So assume one wave is going away from me, suppose I am the source of the electromagnetic radiation going away. So then phase will be reducing. So starts with plus 180, 90, 0, minus, like that it goes. But for the metamaterial scenario, phase will be increasing. Okay, that is the negative phase velocity. And negative thickness device. This is very good feature actually. That means negative thickness, physically thickness negative never be existing, right? Only positive, because thickness means something will be there. Negative thickness means what? It is nullifying the actual thickness, and we are feeling like it is a negative thickness, but it is not so actually. So there is a thickness of the some substrate, but it is whatever the effect which is coming due to the thickness, it is nullifying. Okay, that way it had become negative thickness device and a faster than light propagation. So angle insensitive device. Okay, that also I will show. Okay, single negative can be LHF, left-handed medium or right-handed medium. So if you see this so-called Maxwell equation, del cross is equal to minus dou B by dou T. If you substitute negative mu and negative epsilon in this equation, two equations. Then after this modification, then you see this normal wave K, E, and H will be orthogonal to each other. Okay, like this. But this K had become negative. So that means phase is traveling in other direction. Okay, instead of going forward, going towards source. So that means wave is it's like a person moving away from the point, but he is looking towards us. So that is means he has turned back and going away from me. Like that way, electromagnetic wave will propagate. But in that context, he provides so many benefits actually to us. So now you see. So if you see the metamaterial category, okay, started from first generation metamaterial. So they are basically used to suppress the surface wave. Okay, why surface wave? When there are two antennas, okay, one patch antenna, another patch antenna, when they are kept nearby for some purpose, one is for transmission, another for the reception, then they'll have coupling. It can be through surface, it can be through the conducting surface, or it can be through the radiative coupling. Okay, anyway it can couple the energy. So that can be arrested with the, if you immerse the metamaterial in between, so it can be suppressed. And the planar antenna efficiency can be improved. Okay, so you can provide the EBG or defected ground plane structure to enhance the efficiency. And quasi TEM propagation waveguides. We know waveguides never support the TEM mode, but quasi TEM is possible in a substrate integrated waveguide with metamaterial. Quasi TEM is possible. That means you see, if you see this, whatever I have mentioned here, everything in physical world not possible. But with metamaterial, yes, they are possible. Okay, all are impossible things, they made it possible. Okay, so miniaturization cavity resonator. Cavity resonator, we all know, if it's a lambda by 2 by lambda by 2 in the volumetric structure, it will give the cavity resonator. Okay, but here we can make it more compact cavity, but it will still resonate to that particular frequency only. Then partially reflecting surface. Okay, PRS. So that then there will be a reflecting surface which will use it to reflect the electromagnetic wave in a desired direction. So that partial reflecting surface impedance can be modified so that reflected beam direction can be varied. Okay, so that way also we can enhance the bandwidth of the small antenna. So that feature, if you see, normal patch antenna at resonance, it offers the reactance is 0, right? That's the condition we call as the resonance, right? Where the reactive elements are reactance is 0, that is called resonance, right? But if you operate this patch antenna with low frequency, lower, suppose one patch antenna is designed at 1 gigahertz and we are trying to operate at 800 megahertz. So it will behave like capacitive in nature, because the structure is not sufficient for the 800 megahertz. So it is smaller than the required. That means it will be capacitive in nature. So if I put this patch antenna on the EBG or electromagnetic band gap surface, metamaterial surface, whose reactance is inductive in nature. So both will be cancelling out and it will resonate to 800 megahertz. That means I have kept the size of the patch antenna at 1 gigahertz, but it is now tuning because of the vicinity of the metamaterial at 800 megahertz. Similarly, we can even make it so much compact also. So that means simply make one antenna, bring near to the meta surface, its reactance will change, shift downwards. So that way compact antennas we can make. Bandwidth also we can enhance. Observers we can make. That also a philosophy how it is being done, I will explain. Okay, so this is the first generation. Okay, up to 2010. But later, 10 to 20, so there is a space modulated meta surface. What exactly? If it is a 3D, we call as a metamaterial. If it is a 2D, metamaterial is called as meta surface. Okay, so then there will be meta lens. What is basically lens means? It is the device which is used to enhance the gain. Basically, clocking effect. That one example is there. I will explain. And surface wave based antennas, then meta detectors, meta radomes, near field focusing, holographic meta surfaces, hyperbolic meta surfaces. These are the second generation meta surface. Then third generation they have included the other dimension that is called time. So over the time, surface is modified. That is, there is a technique called reactive impedance surface. So then there is impedance surface whose reactance is modified with time. So now suppose I'm giving reactance is like plus J minus J like that. But later, after some time, I will change that. So after we are changing the impedance, then reflected wave direction will change. Beam width will change. Okay, side lobe will change. Gain will change. Everything we can able to adapt. That means in spatially, that means in any direction you can change at any time. So space and time modulation can be done. So that is a that is the state of art now. So where uncovered zone of now for the 5G or 6G, when there is a customer just behind any big obstacle, but normal electromagnetic wave we cannot able to propagate and provide the coverage to that customer. Then they will keep the intelligent reflecting surfaces periphery or sideway to the walls, so that this electromagnetic wave can be diverted by that surface towards the uncovered user. So that is the state of art now. Digital coded meta surface also we can able to programmable meta surface, digital coded meta surface, all are coming under the third generation meta surface. So if you see to understand and appreciate the meta surface or meta material, we need to understand the basics of the each and every category. Okay, so then PEC, perfect electric conductor. If you try to understand the behavior of the conductor, image current in PEC surface is out of phase. That we know, because whenever E field, E tangential is 0, we know, because incident field and reflected field will be out of phase. Then only EP will be 0. So that is there. Then whenever any radiating element which we are bringing near to the ground plane, then whose input impedance will be 0, because PEC for the voltage it provides the 0. It is a short circuit basically. PEC means whose impedance is 0, resistance is 0, right? So whenever resistance is 0, input impedance of a antenna which is being brought to the near to the PEC, impedance also will be nearing to the 0. So that means we are unable to match it, because we know coaxial cable impedance is 50 ohm, and this antenna input impedance will be changing, right? We cannot able to match it. So that is the one problem. That means any antenna, if you are bringing near to the conducting bodies or ground plane, particularly, whose input impedance will change. So very difficult to match. Okay, so that is happening because of the out of phase is adding the energy, reflected energy is out of phase adding to the incident energy. So net energy is cancelling out, and whose impedance is 0. Okay, so that way. Then another feature of the metal is it is basically storing the electromagnetic energy. If you see the near field nature of the energy which is near to the conducting body, it will be inductive in nature, small inductive in nature. That means it is a reactive field basically. So as I told, matching the antenna input is very difficult. So relative narrow bandwidth, because once field is getting cancelled, once we are unable to match first, and if you bandwidth is very limited. But the other side, if you see perfect magnetic conductor, which is basically open circuit, we can say, we can understand it like open circuit. But physically, it is not available actually, if you speak. But engineering surface, which will provide the nature like PMC. Okay, so whose image current? Suppose there is an electromagnetic wave falling on a surface which is like a PMC, and which will reflect with the 0 phase. Okay, in phase is 0 phase. Then here what will happen? Impedance doubles. The resistance will be doubled. Earlier cancelled because of the out of phase cancelled. Now it will be doubled. Double also problem, because huge impedance and coaxial cable impedance is very small, so very difficult to match. So, but somehow transformer can be used to match that. So that way we can do. But reactance are very difficult to match actually here also. So that means perfect electric conductor and perfect magnetic conductor are not good for the reflectors actually. We cannot use it as a reflector basically. So that means we cannot keep any antenna near to PEC or PMC. Okay, so that way then we have to go for the other surface that is called reactive impedance surface or HAS, high impedance surface. These are the terminology which we are using, and they are the basic elements which we are using for the antenna application. So RIS is superior than PMC. Patch size is lambda by 10 on RIS. What is RIS? Instead of, if you see PMC reflective impedance phase is 0 and PEC is 180. In between, if I use that is called RIS, reactive impedance. So in between, if I see PEC is 180 and this PMC is 0, so if it is at 90 degree, 90 degree can be plus J90 or minus J90. If it is plus J90, it is inductive surface. If it is minus J90, capacitive surface. So both are reactive surface. That's why it is RIS, reactive impedance surface. Okay, so that's what I was telling you, that if I operate this high impedance surface at plus J, okay, J90, and if I make antenna minus J, then they will match. Resonance can be achieved. That means minus 90 of the antenna means very compact actually. So very small antenna you can make, and broad bandwidth also possible. Okay, with unit cell of lambda by 10. So substrate will decide antenna efficiency and bandwidth. Okay, PMC, PEC are not used as a ground plane. Yeah, I told. Then RIS image is distributive in nature. So there is a sinusoidal distribution of the RIS, and so bandwidth is also more. If it is a reactance image is not distributive in nature, if it is concentrated at one particular point, then we cannot able to get the bandwidth. Since it is distributed in nature, so wide range of frequencies, it offers the same reactance. That is the nature of the RIS. So once it is distributed in nature, so it can offer the wide range of frequencies, same reactance. That way we are able to get the bandwidth. So less stored energy, since it is is reactive and opposite reactance we are getting through the antenna. So resonance is achieved. So there is a less storage of energy. With the antenna is having a capacitive load. That's what I am trying to explain. Okay. Then mutual coupling is predominant in PEC and PMC case, but RIC is limited actually, minus 14. So that way mutual coupling also less. Then if you see the metametrial EBG, I think more or less, yeah. So there is a reflection phase. If you see, there are standard EBG. One is EBG, electromagnetic band gap structure. Mushroom EBG, if you take, E tan is finite and H tan is 0, right? So reflection phase at a low frequency, there are two surface waves, TE surface wave and TM surface wave. Okay, so the wave, vertical polarized wave is called TM surface wave, and horizontal polarized electric field wave is called TE surface wave. So we need to then EBG, if you try to understand, I have not picture here, but put the picture here. But if you see the EBG, then via will be acting like a inductor, okay, in shunt, and the gap between the two mushroom EBG is acting like providing the capacitance. Then all put together, it is a parallel LC circuit, right? So where low frequencies inductor is passing through, and for high frequencies capacitor is allowing to pass. Then at a resonance at high impedance, since it is a parallel resonance at high impedance, at resonant condition, it offers high impedance to the electromagnetic wave. So then there is a band of rejection. Okay, certain band is being rejected by the EBG. So that way surface wave is suppressed. Okay, but till from the center of the resonance condition, below that TM surface waves are being allowed because inductor allows the low frequency. So those are vertically polarized. So we are also vertical polarized. So this vertical polarized electric field will induce the current into the via, and that will again produce the magnetic field, and which will be coupling to the nearby via, and so on. It will able to couple the energy. So that way low frequency signals, TM surface waves are supported by the EBG structure. At resonance, nobody will support because both are offering the high impedance. Then at high frequency, TE surface wave, horizontal vector, which is from the each plate of the EBG it will couple the energy to the next plate through electric field. So there is a jump of the field, so that way it is coupling. Okay. If you see the perfect imaging and super lens, so assume this refractive index 1 is air, and there is one material, okay, whose refractive index is negative, okay, so-called metamaterial, okay, double negative medium. And if the wave is impinging like this, conventional media, wave is supposed to go like this, okay. We have seen from whenever wave is going from the low refractive index to the high refractive index, then wave will bend towards the normal. Something he will bend and go. But since it is a double negative, then instead of this is the normal axis of the material, and he is turning this side. Okay, exactly opposite. Instead of going, this is normal plane. Going instead of going that side, if is going, the wave will go this side. Okay, so that means what? So the energy which is supposed to go this side is being allowed to collimate here. Okay, and subsequently one more like this. That means whatever the going is energy is dispersing towards this area is being focused here. That means gain will be increasing. It is like lens effect. It's like a lens effect. Okay, so the gain will be enhanced. Okay, this is called clocking. So the something like you see some fellow is there. This is assume like there is a light source, so it is illuminating like this, and some light is going that way, and it is coming here. Assume there is obstacle here. Okay, one small some mass we kept, and which is not, it's opaque. Okay, behind that we cannot able to see. But since this light is diverted and able to focus here, then this object we are able to see from this place, even though this is covered. Okay, so that means clocking. So that effect is being used in metamaterials to get the super lens antennas also can be made. Now, if you see the evanescent field, as I explained, this is a source of the radiation. As the energy is going away from the source, energy strength will be coming down because of path loss. Okay, 1/4 pi r square. So path loss, energy will be slowly coming down. But the moment it enters into the this double negative material, strength is increasing. But where is the source to increase the strength actually? Then people will surprise actually. So it is focusing actually. Because of that reason, this energy is going increasing. Otherwise, because there is no person to enhance this, there is no amplifier or such that transponder and all. So it is increasing. And from after coming out of the super lens, okay, whatever the metameter lens, it is again coming down. So that way, if you see from here to here, this strength is small and this strength is more here. Okay, that means literally he has not traveled any distance actually. He has not traveled any distance because, okay, if I draw curve like this, almost like this, and once it is entered, little increased, again by that time it reaches here. So whatever the amplitude here, and same amplitude if it is here, and that means whatever he has lost here, he gained here, and by the time he reaches here, same power is available. That means he has not traveled any distance. That's what I told. It is a zero thickness device. So that is also possible, because whatever you are losing because of the dispersion of the energy, as per the Huygens principle, energy will be dispersing in 3D space. Okay, that whatever we are losing, the moment the energy is entering into the metamaterial, he is gaining that because of all whatever the diverted field is being collimated, and he is gaining that energy. Okay, because all gain is gain means it is all about relative to the isotropic. Okay, so that way negative thickness devices also can be built. Okay, then if you see the Doppler shift reversal, right-handed system, when we are going away, and assume there is a crust of electromagnetic wave which is going away from the source, and when you are moving in front of you, there is a compression of the wave. But when you are in the left-handed material scenario, when you are going, wave is going away, but there is expansion. That means wave is coming towards you and the energy is going away. So this is the opposite actually. So that's what I'm trying to explain. So, and this is the clocking. Okay. So whenever wave is plane wave is incident and it is coming, and the moment he has seen there is obstacle and he has gone like that, but immediately he has corrected his path and coming. That means if you see from here to here, it is visible actually. Light is falling like that, but this as if it is like this object is not available. So that's what the clocking. Okay. So that way also mathematical can be built. And similarly, if you see this example, plane wave is instanting like this, and this is the transmission of the energy, and for different angles it has incidented. Then in between sandwiched with the metamaterial, who who is doing a reversal of the actual media. That is like we have seen earlier. So whatever the wave phase reduced within this right-handed system, it is being compensated by the left-handed system, so that phase, by the time energy is reaching the other side, phase is almost same at the source. Whatever the suppose phase of the wave source at the source is 0 degree, then after coming out of the this total structure also 0 degree. That means he has not traveled any, but physically there is a thickness, but he's electrically it is showing that I have not traveled anything. So that is called zero thickness device. It has got a huge application in electromagnetic. And similarly, if you see the conventional transmission line where there is a normal two-wire transmission line, if you see there is a inductor. Any wire will have the current, and due to eddy current, it has got the inductance, right? So, and between the two wires, okay, live wires, there will be capacitance, right? So that normal series inductor and shunt capacitor is the normal conventional transmission line. But when this transmission line is breaking, okay, in between some gap if we provide and continue to go like that, break, then series capacitance will come. Okay, and in shunt capacitor, hello, am I audible?
Sir, audible, sir.
Yeah, sir. Yeah.
Audible, sir.
So
Yes, sir.
yeah,
Proceed, sir. Proceed.
yeah,
Hello?
okay. Yeah. So similarly, if you keep any inductor with from the live conductor to the ground, okay, so then it will become then there will be backward wave will be there. So that means effectively what will happen? There is a series inductor and series capacitor, and a shunt inductor and shunt capacitor. That means both will be there are two resonance circuits. So this is a series resonance circuit, and this will be shunt resonance circuit. Okay, so then they will act like a pass filter and band stop filter. So band then instead of low pass filter, high pass filter, they will become band pass filter like that. Okay, so it is called CRLH, composite left hand right hand transmission line. Okay, so because normal transmission line is a right hand transmission line. Now because of introduction of this series capacitance and shunt inductance, it had become left-handed system. So both put together left hand right hand transmission lines, composite left hand right hand transmission line. So what is the advantage of it? So what is the phase which is losing because of the traveling inside the conventional transmission line can be compensated with the backward transmission line, so that the effective phase will be 0. So that means what? Phase shifters can be built. Okay, CRLH is a potential source to build the phase shifters. Okay, any phase you can able to do with the extra introduction of these two elements. So it is the best tool. There will be multiple technologies like microstrip or SIW or any technology you can use and try to build the phase shifter using metamaterial. And this is the what I was mentioning. So it is supposed to be with the normal material. It might be going like this, going away from the normal, but continue to go. But it is turned back, and that way it is clocking effect is coming actually. So some of the examples, if you see, pattern improvement of monopole antenna. So normal, this is monopole, this is a ground plane. Okay, whenever you are exciting the monopole with coaxial cable, so it will radiate. Okay, so along the wire there is no radiation. Okay, so assume there are positive charges on the monopole and negative on the ground. So there will be field, okay, away coming away from the monopole. like vada structure. So will be forming. Okay, fine. So that is something like this. So whenever field is coming to near to the ground, because as I mentioned, so field is coming like this, right? So assume all the time, rule of thumb, electromagnetic radiation, okay, that is wave vector k, direction will be perpendicular to the E field. So here a positive charge is there, negative is there. So there is a field like this, right? So that means radiation is going this way, this way, this way, this way, this way. But along the surface, it will not go, because the surface offers the 180 degrees out of phase signal, then it will reflect back. But for the vertical polarization, yeah, it will flow. That's why there is a energy which is going along the surface also. Okay. So and there is a null in the peak. Okay. So then if you see the analysis, induced currents are restricted to localized regions. So it acts like a PC ground plane at the out of band region. Suppose this EBG, this monopole is kept and it is covered with EBG. Okay, how it will behave? The pattern will change like this. So there is a smooth pattern which is lifted off actually. So this ground plane effect is reduced actually. Okay. And if you see horizontal dipole on EBG, I told there is a monopole, same monopole, vertical, but it cannot be kept like this for the aircraft. Suppose I want to put the monopole antenna on the aircraft or a vehicle, some normal car, we can keep. Since a car, no problem, we are able to keep. But no, but some cases I don't want to keep like this. So then what I will do, I will bend it. Then the moment you are bending towards the ground plane, whose input impedance will change. That's what I explained, right? So now what will happen, you see. Now instead of bending like that, in between we are keeping the EBG. Okay, then what will happen? EBG offers the high impedance actually. So I told high impedance, he will offer the out of phase, in phase actually, instead of so if this dipole monopole is nearer to the PEC, then reflected field will be 180 degrees out of phase. Since it is covered with EBG, whose reflection phase is 0 degree, that means its resistance is doubled, reactance also there. Okay, fine, but it's a more compact now. Instead of vertical, it is occupying less space. Then what will happen? Then pattern will be nice pattern we are getting with 7 dB gain. That means almost like a patch antenna pattern we are getting because of the high impedance surface. So so then here we can say it is a compactness can be achieved. Okay, so it is able to support the LP, and circular polarization also can be realized with this. Okay, but the gap between the monopole and EBG should not touch it actually. The moment if you touch it, it will be short circuited. Then resonance we cannot able to achieve. So there will be some gap is required actually. And if you see the diffraction control, normal this is waveguide, coaxial to waveguide adapter, we can say normal waveguide. Okay, so operating in T10 mode. So it has got something like a pattern like this, E plane and H plane. So then it is covered with the EBG. Then what will happen? Normally, if you see radiation pattern of aperture antenna in a conventional metallic ground plane, then if you see the E plane, this is H plane actually. E plane, there is a wide E plane actually. Okay, there is a wide E plane because in the E plane direction, electric field will be vertical polarized. So E normal is continuous in the metallic objects. That's why there is a like this. Then radiation pattern of aperture antenna in the high impedance surface. What will happen? High impedance surface, as I told, at band, exactly at the band of the EBG, it suppresses both polarizations, TE and TM. So that's why this vertical polarized energy is not at all available here. So the same pattern is available. Then another way, suppose if you change the EBG, now in this scenario, the antenna and EBG both are in the same band. But if I change the EBG structure such that it is being operated at the TE band, which is basically below the resonance. Okay, or otherwise we can say waveguide, I am changing the dimensions such that it is TE band of the EBG. Then what will happen? So it will enhance the beam width of the H plane actually. H plane here narrow and E plane broad. after the introduction of the EBG, both are same, symmetric, because this EBG is not allowing any of the TE or TM wave to come out of the structure. This the surface current is stopping. So only radiative coupling is there. That is, both are more or less same beamwidth in both planes. But once we are operating below the resonance of a EBG, okay, waveguide below the resonance of EBG, then H plane there is a coverage increased. So that means some of the applications where wide beam antennas are required. So this kind of behavior of the EBG can be used. Okay. So then reflective beam steering. So we have seen the EBG, and each EBG is connected with other nearby EBG with one diode. Okay. So diode can be operated digitally controlled. Okay. So this diode can be switchable. Okay. Based on the diode on and off condition, some of the EBGs can be, so this pattern can be manipulated actually. So some of the diodes can be on, off, like that, so that effective impedance of the EBG can be changed. So incoming wave can be reflected in any desired direction. So if you see this graph, okay, this is the plane of the surface. Okay, so normally if you see any radiation, reflected wave will be depending on the plane of the phase. Okay, if it is normal plane of a phase, if it is a flat, then reflected wave will be exactly going back into the same direction. If phase front, we can say phase front is tilted like this, then general thumb rule will be perpendicular to this structure, there will be a radiation. Okay, since phase front is like this, then radiation will be this direction. If phase front is like this, then radiation will be this direction. So that means we are able to change the phase of the EBG using the diodes such that phase front is manipulated all the time, okay, dynamically, so that reflected energy we are able to divert. Okay. Then if you see holographic artificial impedance surface, so these are it is basically copper clad sheet, one side grounded, other side there are patches. Okay, but they are engineered structure. Okay, they are engineered small patches, but with some coding we are able to keep like this. Then what will happen when you are keeping, this is the monopole, and you are keeping monopole other side of the cylinder. Okay, so this monopole generally he will radiate energy like this, right? Like this. Fine. So he will go, this energy will travel like this, like this, like this. Fine. But this energy, whatever is falling on this, along the surface is traveling. Okay, along the surface is traveling, but there are EBG, right? Okay, I am artificial impedance surface. So along the surface is traveling, and each time when there is a discontinuity, we all know that whenever current carrying conductor, okay, some current is flowing on the conductor. So whenever conductor is having discontinuity, it tends to radiate. That means wave is detaching from the structure. So similarly, here also, this energy is falling onto the surface, and since this impedance surface is having the discontinuity, but it is a systematic planned discontinuity. So each and every place it is tend to radiate. So this structure is made such that this radiation is constructively adding. That's why there is a plane wave. We can say all wave vectors are in plane. So then energy will be constructively going in this direction. That means exactly what we have achieved. Actually, see, monopole has been kept in this side. Suppose he is supposed to give the coverage this side, but he is giving coverage this side. That means diffraction limit also we can able to exceed. Okay, that is the beauty of the holographic impedance surface. So otherwise, without metamaterial, getting coverage to the other side of the cylinder is never possible. But that diffraction limit also, okay, we are able to achieve with the metamaterial. Then if you see the photonic band gap structure, normal transmission line. So this black is a normal transmission microstrip transmission line. So if we are feeding this side, and we are able to collect this. Okay, S12, if you see, the insertion loss will be very small in the normal microstrip transmission line. But if you embed some porous kind of holes in the ground plane, what will happen? So when they are arranged in a systematic way with some kind of pattern like a square pattern with some gap, then they will provide like some band notch nature. Normal transmission line is a basically all pass filter. It never stops any frequency. But since there is a systematic pattern embedded in the ground plane, okay, so they will try to stop some band. So that means what? It is a band stop filter. So some of the cases in your communication system or anywhere, we are trying to notch some bands. So that nature can be achieved with this kind of metamaterial. Okay, they are basically periodic structures. Certain bands are prohibited. Okay, used to improve radiation pattern. Broadband observers, FSS, frequency selective surface. Frequency selective surfaces are the surfaces which are made with it can be made with the dielectrics or metals to allow only particular band of frequency. Other bands it will be rejecting. So that is very good for the LPI, low probability of intercept scenario. So where we are not exposed to the enemy. Okay. So there's the suppression of the harmonics in antennas. The antenna, if you see, it is basically a resonator, but it will produce the harmonics of its own frequency. Suppose there is a 1 gigahertz antenna, then it will it has the capability to send radiate 2 gigahertz, 4 gigahertz, 8 gigahertz, like that. All harmonics will come, but their harmonics capacity will be lesser. But still, there is problem at some other band. So then those harmonics can be suppressed with DGS, defected ground plane, photonic band gap structure also. Okay, so then if you see the other application of the defected ground plane structure, there is a normal patch antenna with microstrip line feed. Then ground plane, there will be cutout provided. Okay, so some material is scooped out. Then on the ground plane, if you see, then the moment you exit the patch antenna, the surface current will flow, because the current doesn't know which direction he has to flow. Where there is a low impedance surface, he will flow. All directions he will flow. So for a counter to this, other current 180 degrees out of a current will flow in the ground plane. But the moment it is flowing in this ground plane, he has seen one vacuum. That means removal of the copper here. That means he is facing discontinuity here, and he is trying to take another path. Like this, he will travel. That means effectively it is currently taking longer path to travel. That means whenever the current is taking longer path to travel, then structure is getting miniaturized. So electrical length will increase, and we can say antenna is compact in nature. So that way, so people might be thinking that if you put a hole on the patch antenna, it will be compact. That is correct, but the same effect can be achieved by providing the hole in the ground plane also. Because ultimately our aim is to provide the longer path for the current. If you put slits here, suppose there is a horizontal slot here, then current will take all the way this much path, and so that a compact antenna can be built. But in this process, we should see that pattern should not get disturbed. So the way, what is the pattern we want, whether it's clean pattern we want or back lobe we want. Now here there is a back lobe. So that is the poor here response. Okay. So what do we want actually? Good pattern is required. How much back lobe is required? How much side lobe is required? And what is the cross polarization expected? Bandwidth are we getting? Like that also we have to see well when you are making the antennas. Okay. Then yeah, what he has done, research. This is one of the paper I have taken. So then he has the interdistal slits has been provided in the patch, so that he is providing a series capacitance. Okay, series capacitance. That way also frequency. If you see, initially it was designed here, and later because of each introduction of this series capacitance, then slot here in ground plane, and it modified this slot in the ground plane. Ultimately, is able to get 3.3 gigahertz. So 10 to 3.3. So that these are the miniaturization techniques using the metamaterial. Okay. So 70% of size reduction has been achieved. Then if you see, there is a source here, and with the quarter wavelength height, there is a metamaterial unit cell has been kept. So it is like this. Then what is exactly happened? This is patch antenna, which is inside this housing. Then patch antenna has got a normal pattern, assume 70 degree by 70 degree pattern. Okay, like this. Then that pattern, this antenna is excited, and it is covered with one superstate. which is covered with a meta surface superstrate. Okay, so then what will happen? Normal energy for the normal plane wave with 0 degree phase, direction of 0 degree, you will not disturb. Okay, this lens, it will continue to propagate like this. Then whenever the wave is going away from the source, this direction and this direction, so they will be sent towards this normal direction only. So that's what we have seen, that negative Snell's law, negative. So that way all the energy is being collimated here, so that he has reported the gain. Okay, gain in the literature. This is the super lens which he has kept, and the same time he has achieved the bandwidth also. 5 gigahertz bandwidth has been reported here. Okay, then mathematical, if you see the category wise, there are so many mathematical, everything people are saying mathematical and all. So then category wise, if you try to analyze the frequency selective resorber, so it is basically FSS only, frequency selective surface, with a certain band you will absorb. Okay, whatever the band you want, other than that he will absorb, and the particular band he is able to send. Okay, so that means it is offering the low RCS. Okay, where suppose I am operating at 10 gigahertz. So other than the 10 gigahertz, but he will receive every frequency. Okay, 1 to 18 gigahertz, everything he will receive. But at 10 gigahertz, he will able to send. So that is the nature of the frequency selective resorber. Then automatic band gap structure. So one typical example is mushroom unit cell. So he is able to provide the compact, because when you are using the EBG as RIS, reactive impedance surface, then compactness can be achieved. And similarly, isolation also. So whenever you are embedding in the mushroom unit cell between the two patch antennas or any monopole antenna or any antenna, then isolation, because since it is topping the particular band, so isolation can be improved. And beam scan limit improvement. So that is what we have discussed, the diffraction limit. So when you are covering this with holographic meta surface, we have seen. So diffraction limit can be, so uncovered zone also it can able to cover the, it can able to provide the coverage. So okay, so the coverage near the grazing angle, that's what. So otherwise the normal electromagnetic wave near to the metal surface, it cannot able to travel. When it is a horizontally polarized wave near to the metal surface, it cannot be able to travel, because the moment near to the metal surface, he is providing 180 degrees out of his vector, so it's cancelling out. But if it's a high impedance surface, it comfortably can travel along the surface. That means along the metals, energy propagation is possible. Okay, once it is engineered such that, so near grazing angles also coverage is possible. Then another important of the mathematical is zeroth order resonance. So what is this? If you make epsilon near to 0 and mu also near to 0, then what will happen? Reactive impedance will, the refractive index will be 0. So when refractive index is 0, then velocity will be infinity, right? Yeah. So, and C is equal to n lambda. Frequency into lambda. So then lambda will be infinity. Frequency will be frequency remain constant, and then velocity will be infinity, right? So lambda infinity means what? It is a almost zero frequency. So for to get the, if you get the epsilon 0 and mu 0, then your lambda will be near to 0, near to infinity. That means low frequency. So that means independent of frequency. Any structure you can able to make to small structure. Say suppose 1 megahertz antenna. Then 1 gigahertz needs 300 mm. So 1 megahertz antenna needs 1000 times the 300 mm, right? 300 meters, right? So 300 meters antenna by 2, if it is half wave dipole, then 150 meter antenna is required for 1 megahertz. So that means for the zeroth order resonance, if then you are able to make small antenna also can operate at zeroth order resonance, because of the epsilon you are making near to 0 and mu also making near to 0. So that is possible. People have reported that. So reactive impedance surface, as I mentioned, you make reactive impedance surface inductive nature, and the antenna whose input impedance should be capacitive in nature, so that if you are bringing a nearby, then they will become resonant and a compact antenna can be made. So artificial magnetic conductors, again compact, Fabre-Parrot for gain and bandwidth enhancement, DCS, they are able to, since they are providing the different path for the current, longer path, so that compactness can be achieved and efficiency also can be achieved, but poor front to back ratio and bandwidth also can be achieved more. And VBG, particularly harmonic suppression in the circuits they are using for to stop this particular band, harmonics also they are able to suppress. Now, if you see some of the examples, a split ring resonator, he is offering the epsilon negative. Okay, epsilon negative. So whenever you are sending the automatic wave in this direction and picking up here, then it offers the particular band of frequency epsilon negative. Okay. So similarly, for this metallic rings rod, they actually split ring resonator will offer mu negative, but this metallic rods will offer the epsilon negative. Okay. So this is another split ring resonator. People have demonstrated coupled resonator actually. So where epsilon is negative and here it is mu is negative, and here he will offer the epsilon negative. And if you put both together, then both negative can be achieved actually. Now this is one of the example where complementary split ring resonator and this pole electric rods are, we can say, if it is a planar structure, thin wire of track, copper track. So here this track is offering epsilon negative, and this split ring resonator is offering mu negative. Both put together, there will be both negative. Then as I mentioned here, if you see for the left-handed system, series capacitance and shunt inductance can be achieved with this configuration. Okay, so this is the left-handed system. And one more practical example, if you see, there is a microstrip line feed. If you see, this is the microstrip line feed with the broadband cap for impedance matching, and which is exciting the slot. Okay, this is copper clad sheet where the bottom there is a ground, and this is also another other side of the copper clad sheet, and there is a slot in here. So this slot is excited by this microstrip line. Okay, this slot is excited by microstrip line. That means effectively it is a slotted antenna, single slot antenna. We know single slot antenna will give 2.5 dB gain, right? Fine, but I am not happy with the gain, so I want more gain. Then what I have done? So I have covered with so many mushroom unit cells. Okay, then what he is doing? So this center energy straight away it will go, but the energy which is going this direction is being diverted to this direction because of its double negative nature. Okay, the energy which is going this side is again diverted to this side. So that way he is able to get the gain of 11.9 dB. Okay, 11.9 dB we got the gain with 24.3% bandwidth. So bandwidth also huge, gain also huge. So that how it is possible? Because of the, we can see this structure. If you see all put together for one length assume, and each two one more length. So that means harmonics, multiple harmonics of the structure are being excited by single slot. So that means multiple harmonics are also we are able to excite with the single slot, so the bandwidth is enhanced. Okay. Then if you try to understand the boundary condition of a ground plane, even PEC or PMC, then a horizontal polarized antenna. If you see, these are all famous, everyone knows actually. So electric field inside the electric conductor, it will be opposite in nature. If it is a magnetic, they will be in phase actually. Okay, so you see, electric field E tangential is continuous here, but H tangential is image. Magnetic field is opposite in nature for the PMC boundary. Okay, that's what I'm trying to explain. Okay, then if you see super directive antenna array, so this is a normal one loop antenna, square loop antenna, square loop, and whose property, if you see, there is a negative. Okay, this is the mu negative. Okay, right? Mu negative has been provided by this small loop, 0.05 lambda size loop, and which is being kept in between the two patch antennas and realized on phase array. Okay, but now the antenna, you see, if you see 1.18 lambda size, there are 5 elements. Very compact size actually. It's all-time high actually. So we cannot able to keep microstrip patch antennas such a very small spacing in small zone. Okay, in lambda, 1 lambda generally we keep only 2 elements. Okay, so maximum 3. But here this researcher is able to keep 5 elements within 1.18 lambda size. So that is a very good achievement. So that super lens we can 60 we assume, then 2 elements will give 9 dB, and 2 more if you add 12 dB, and 1 more. So almost 13 dB gain can be achieved with 1 lambda size. Okay, that is called extending its. That's why these kind of antennas are called super gain antennas, super lens antennas. So super direct array. Okay, so that is possible because of the immediate to the antenna there is a one device which is a basically insulator, which is suppresses the coupling of the antenna. So then only constructive addition of the energy is taking place, and then there is a huge gain in a particular given direction. Okay. Then if you see that, try to understand the theory behind the observer, microwave observer. So this is standard formula for observer. Observability is equal to 1 minus S1 reflection phase. Okay. Reflection coefficient, and S21 is the transmission coefficient. So this is normal copper clad sheet with some pattern front side, and rear side is covered with the ground. That's all. So nothing else. Okay. So, and if I am able to send the electromagnetic wave here, and since it is covered with the metal, nothing will come here. That means S21 is 0, right? So that this is gone. Then observability is equal to 1 minus S11, right? And then if I put S11 also very low, because the ideal S11 is minus infinity, right? So that means what? If I am able, whatever I am able to send this energy, if he is able to go inside and nothing is coming back, then S11 also very low. Then we can neglect this, right? Then observability will be 100. That means 100%. That means what? Ideal condition of the observer and go inside, and you should not send to this side, or again you should not send it back. That means what you should do? You should observe that. Okay, you should store that. You should dissipate that. So there are 3 things. Try to understand. So one is you should accept. So when he will accept, so what is the impedance of the free space? It's a 377 eta. Okay, for the normal TE mode, TEM mode, and free space is a free space impedance is 377. Then whatever the pattern which we are making to observe as an observer for the microwave observer, so whose impedance also should be same. Then only this gamma is Zin minus Z naught by Zin plus Z naught. Same story. ZL minus Z naught by ZL plus Z naught. So reflection coefficient. So he will observe everything. So that means this whatever near to the free space impedance. That is first condition. He will observe everything. He will allow first everything. Fine. And he is going inside, and he is hitting the metal, and he may come back. But he should offer now resonant nature. It should be trapped inside the observer. It should not come out. If it is coming out, then S1 will be poor. So that is the condition to make the observer. Okay. So if we are able to satisfy this condition, then micro observer can be built. Then a metametal observer are very thin of this kind of different sizes will be there. So then this is the condition. So this researcher is trying to so he got 96% absorption. Okay. Then this ultra thin, whose size is lambda by 20. So very fine, because if you see the mechanical normal Okay, then metametal absorber we can able to make very thin, but they are actually narrow band initially when they are designed, but now the techniques are there to improve bandwidth. Now you see another passive single and a multi-band metametal absorber. If you see, we have seen this is small and this is bigger. These two are belongs to one band and these two are belongs to other band. That means two bands can be absorbed. So you see, two bands can be absorbed. So like that, we can able to play with the multiple bands also. We can able to absorb if they are put nearby. Then what will happen? Broadband. If you are making nearby, then these two can be merged so that broadband can be achieved. Now you see here, yeah, this is brought nearby, then broadband observer. Okay, and the captured by observer, and it should be it is being trapped inside the observer. Fine, but it cannot store longer time. It should dissipate the energy. So who is the culprit? Means who is the basic element to dissipate the energy? Resistor. So there should be a resistor to dissipate this energy, so that whatever is absorbed and stored, that will be dissipated as a form of heat. So there is a for all observers should have the resistor actually. So that then people have it has been evaluated. Evaluation is like this. So they have incorporated the resistors actually. Okay, there are 4 resistors in each unit cell, so that broad bandwidth is achieved actually. So that means he is never. So there is energy trapped inside the observer, and which is being dissipated in the resistors, so that nothing is coming out. So that way he is able to absorb the full energy with a wide bandwidth. Resistors and all with gap with the diodes you can able to manipulate this gaps and all, so that it can be tunable observers also. Mechanically you can able to tune, electronically you can able to tune using the pin diode, and MEMS switch also, anything, because the tuning mechanism are it is same for the like antennas, how we are able to provide the tuning mechanism. Similar mechanism can be adapted for the observers also. And coming to the other technologies, the surface wave based meta surface. So what exactly, if you see in this picture, there is a one monopole, okay, normal monopole. If you put normal monopole, its length should be lambda by 4. Everyone knows. But I want to very short monopole. What I should do? I should reduce the height. Okay, what I will do? I will put like this. Okay, it is also monopole, but it is like this. That means it will provide the same resonance. So I will extend this side also, all sides. So like top loaded monopole. That means one planar sheet I am keeping on the monopole. So it will act like top loading monopole. So compact size monopole can be built. That's people have demonstrated long back. So same monopole. Now this monopole is radiating energy. Which direction? You will not radiate this side, because ground plane is the other side, bottom. So this is the monopole. So this monopole and this everything put together is a live element, and ground is here, right? So there is a field in between. So that means this energy is, if whenever the field is like this, then radiation will be perpendicular. I said, right? So this side, this side, this side, all along the surface there is a wave energy is going. So that way, if you see, there is a monopole. So along the surface, along the surface, along the surface, along the surface, all directions. Fine, but one more we discussed that whenever electromagnetic wave is propagating along the surface, when there is a discontinuity, it tends to radiate. It tends to detach from the surface. That's what we discussed. Now it tends to detach from the surface and radiating. But we are keeping this. If you zoom, this it will be like this. So this surface is kept and engineered structure such that whose radiation is constructively added up, okay, for purpose. Okay, now this researcher, how he has done, he want to make a pattern like this. Okay, so that way he has made, then he got this kind of pattern. So any pattern you can able to do. That means simply it is called meta surface. Okay, so you are able to programming this meta surface such that any monopoles pattern, null pattern, sum pattern, tilted beam pattern, fan beam pattern, anything can be achieved. For example, if you see, this is a dual polarized antenna. Normal till now, we know that one aperture will give only one sense of polarization, either right hand circular or left hand circular. But from the same aperture, this researcher has produced the two sense of polarizations. If you feed here LSCP and if you feed here RSCP, that means what? For the same purpose, communication purpose, if I want to send a RSCP signal to, suppose, ground station to satellite, RSCP I am sending, and satellite is again sending RSCP, I am able to receive with the RSCP, no problem. If satellite is sending LSCP, I should have one more antenna actually to receive the LSCP signal till now. But now with this antenna, simply feed here, you send RSCP, and from receive LSCP you will receive. No extra, so it's the shared aperture antenna. So this is the breakthrough actually, and two orthogonal polarizations coming from the same aperture. So this is the beauty of the meta surface. Okay, and that is how it is happening actually. So here, if you see, this is monopole, normal top loaded monopole. I said, then the energy is electric field is like this, and propagating along the surface. During this time, it is basically leaky wave antenna. So is facing the discontinuity and trying to radiate. All this energy is constructively added up and he is getting the RSCP. Fine. But for this fellow, its counterpart, 180 degrees out of phase current is traveling along the bottom of the meta surface on the surface, ground plane, and along, like this he is traveling, and he is traveling exactly opposite to this. So he is getting other sense of polarization, that is orthogonal polarization. Okay. As well as LSCP, both sense of polarization. Okay, so similarly, this is different pattern actually. So real polarized. Yeah. Okay. Oh, sorry. What is happening? Oh. Yeah. So dual polarized metasurface antenna. So this is also different structure actually. Yeah. More specifically, it dwells into the two surfaces can be characterized by support surface modes of equal phase velocity but different polarization T and TM. Okay, so yeah, if you see the MIMO antenna, MIMO meta surface, what is happening? See, this meta surface has been provided with engineering actually. So some of the portions he has removed some of the portions. So it is coded meta surface, digital coded meta surface, where if you feed it different ports, okay, so then different beams can be. It is like imitating the Rotman lens. Rotman lens, if you see, based on the path delay of the substrate, okay, then beam direction will be changing. Okay, similarly, if you see, there are multiple connectors, yeah, and each suppose if you feed here, then since this energy along will be different, so that these elements inside the antenna will get the different phases, and by changing the inputs, then it will get changed actually. So that way, then we can able to switch the beams actually. So that way we can able to utilize this metamaterial. So these are the references actually that I have. I'm done actually. Okay. Any doubts? You please ask.
Dear participants, if you have any doubts, please ask sir. Sir. Dear participants, you
Sir,
can
I
ask.
have a query.
Hello?
Good evening, sir.
Yeah. Please.
So actually, for metamaterial, what about the frequency and the relation? Because every antenna is related by certain frequency, but metamaterial, whether it is frequency independent antenna or what, sir?
No, purely dependent. Basically, it started with frequency dependent highly, but later people have made it broadband also, so we can able to achieve now bandwidth. Okay, otherwise it's a highly resonant antenna. So frequency dependent antenna.
Sir, one more question is posted in chat box, sir.
Yeah.
It is by Nidhi Tiwari. Sir, when we are analyzing a metamaterial unit cell, the epsilon or mu or both needs to be negative for entire operating bandwidth. That is the question, sir.
Correct. Na? If you want to see, that's what people are saying. Once we say bandwidth means all parameters should meet. That's what we call bandwidth means. Okay, so it should give equal gain, but no antenna will give equal, but trade-off less than plus or minus 1 dB gain or less than 10 dB return loss. Okay, 3 dB beam width of 60 degree with plus or minus 5 degree, like that. Some condition we only have to put, and within that it should meet that way. So that way we can say this is the bandwidth of the antenna.
Sir, one more question, sir.
Yeah.
What is the difference between analysis of metamaterial and metasurface antenna?
That's what I told now. Metamaterial is a 3D. Okay, 2D metamaterial is called metasurface. Where this via third dimension, via will not be there in the metasurface. Only normal copper clad sheet. If you take, there is a ground plane in between substrate and top there is a patch, right? Another layer. On the top layer, we are somehow we are etching something, some square patch, circular, like that we are keeping. So this is metasurface. If you put via, it will become metamaterial, like that.
More question, sir. One more question, sir.
Yeah.
Will metasurface antenna provide high gain and high bandwidth both, sir?
Yeah, I have shown one example where slot antenna is cell EBG, and we are able to achieve 24. That's not my paper actually. Okay, I have simulated one of the research paper. So he is able to achieve 24% bandwidth and 12 dB gain. So that means gain also can be enhanced and bandwidth also can be enhanced. Both are possible.
Sir, what is the frequency, sir? While we are reaching the high gain, what is the frequency?
Any frequency we can do, madam. It is not it's not frequency dependent, no, it's a scaling, frequency scaling, so that will work actually. So if I am able to do one antenna at 1 GHz, it will work at 10 GHz also. Okay, it is immaterial actually. So this researcher has demonstrated
Sir,
you see.
Sir, actually,
Yeah.
I have designed one antenna, sir,
Yeah.
with FR4 substrate
Okay.
at 10 gigahertz, sir.
Okay.
Now, can I increase the band, sir?
5
to
gigahertz,
20?
madam. 5 gigahertz. Yes. Yeah. Can you increase?
Now, it is radiating at 8 gigahertz, sir.
Okay.
Now, can I increase the band by adding metamaterials to that antenna, sir? FR4 substrate antenna.
No, substrate immaterial. Okay. But FR4 is lossy. Why you selected actually? But efficiency will come down. Okay. If you operate FR4 at 10 gigahertz, efficiency will be poor. No problem. Right? And you are designed at 10 gigahertz and it is tuned at 8 gigahertz. You are telling, right?
Yes, sir. Yes, sir.
And then you want to make it again to tune at 10 gigahertz, right? Yeah, that's possible.
Hello, sir.
But mathematically, you had to use it to make a compact antenna. You have designed 10 gigahertz antenna, which is now you are getting at 8 gigahertz, right?
Yes, sir. Yes, sir.
And then if you apply mathematically, it will further, it will bring down 6 gigahertz, 5 gigahertz also you can make it. Now, same structure. 10 gigahertz antenna with mathematically, it may tune for 5 gigahertz, 4 gigahertz, like that.
Can we increase the band, sir, to 24 gigahertz or 30 gigahertz?
No, that why you want mathematical? If you size, if you reduce, it will go higher side.
But losses are also increasing, no, sir. When I am
Mathematical
decreasing,
cannot.
when I'm
don't use for high frequency. No. See, some of the things people need to know. At high frequency, FR4 will not work.
Yes, sir. Yes, sir.
What is the last tangent of FR4?
2.4.
No, last tangent 0.02.
Point
Very
0
huge loss. 10 delta is very poor actually. So
Yes,
you cannot operate. And at high frequency, even thicker substrates also you should not use. Thinner substrate you should use, and low epsilon R substrate you should use. Okay.
sir.
Maybe
What is the
20
best, sir? What is the best material, sir?
Artiduride only. Artiduride 5880. You are researcher.
Yes, sir. Yes, sir.
You may not get LZ material. Otherwise, LZ material is there. So that is even less. Epsilon R is less.
Yes, sir. Sir, one thing,
Normal
sir.
Artiduride you can take 5880.
Sir, can I get that artijoide from market, sir? In anywhere? Where can I get that material, sir? Artijoide. Can you suggest me?
Yeah. I can tell you. My mail ID you note down. I'll tell you sources. Samba NIT. SAMBA@gmail.com.
Sir, 1 minute, sir. I am writing, sir.
Yeah. There is a Icon Electronics. ICON Electronics.
Icon, sir. Okay, sir.
Some more also I can tell you.
Sir, chat box, can you give that one, sir? Mail ID.
Yeah, I'll see. Okay, I'll see.
So that we can save it now, sir.
Yeah. Chat box.
Thank you, sir. Thank you.
Yeah.
Hello, sir.
Yeah. Please.
Yeah. So thank you so much for a nice lecture on metamaterial and metasurface. Sir, I wanted to ask something about the dimensions of a metamaterial unit cell. So how to calculate the dimension of metamaterial cell for a particular frequency? Because for the antenna we have the calculations, but for metamaterial, how to decide for a particular frequency what should be the proper dimension of a unit cell?
Which unit cell you want?
It is a metamaterial cell only, sir. It simple patch, not SRR or CSRR, but a simple patch like you shown for the square patches, which is
Okay.
placed
That
periodically.
mushroom EBG, right?
Yeah.
Hello.
Yes, sir.
Mushroom EBG, right?
Not mushroom EBG. It was a square or hexagonal. What you showed in the PPT also in your PPT. It was a hexagonal shaped, periodic hexagonal, and square patches used as a metal surface.
Yeah. That is not my design, madam. I have taken from literature only. Okay. So there are plenty of papers. You are discussing about this, right? This kind of, you are able to see my screen?
No, sir.
No, okay. EBG, there is a book, and for mushroom EBG, there is Balani's book. It has been given. Okay, engineering electromagnetics by Balanis. So that book,
Okay.
Sir, you can
Okay.
share your screen, sir.
Yeah, 1 minute. So you are telling about these unit cells?
Yes, sir. Like this only.
Yeah. This is not such easy, madam, actually. So you have to read the literature, actually. Simple, we cannot tell.
Okay.
It will be lambda by 6, lambda by 7, like that. But
Okay.
not that much easy, actually, for us also, because it's a modulating surface. Each location unit cell size will be different. They are not constant, okay? And
Okay.
if you see that angle is rotating, okay?
Yes, yes.
If you see ex-APS Society chairman of IEEE
Okay.
is the author for this paper. So they have done it, actually. So you can
Okay.
Google it, actually. You will get.
Sure.
But straight
Sure,
away,
sir.
it will
Sure.
not come. It will not come straight away. Okay. I cannot
Yeah.
also tell you.
So one thing more I
Somehow,
wanted to ask, like in this structure, there is a rotation in for every structure, but suppose there is no rotation and that is a fixed structure. So I just wanted to know, like when we are analyzing for a unit cell to check whether it is behaving as a metamaterial or not, after it is behaving as a metamaterial, like I'm getting the refractive index value, and then again I am moving towards antenna and I'm making it a periodic one. So then again, I need to analyze the complete meta surface, or the unit cell analysis is enough. And after that, I can use the structure as a periodic to make a meta surface antenna.
level only you have to analyze. Later, you have to work like antenna level. So no need to see, because all the elements which you are required to get the required phase, you have to calculate it unit level, and you have to.
Okay.
And these are all how you will keep actually each unit cell. Suppose in this scenario, if you see, there is a code. Okay, we have to program it, actually. Otherwise, simply you cannot place like this, right? There are so many
Okay.
elements, and so there is a code required. So if you see, I think I'm also trying to get this kind of things, but we are writing our own code. But we have to work like that only.
Okay.
But
Okay.
you can work with people like CST Micro Studio, na? Or
Yeah.
HFSS. They will provide, actually. There is a provision in the CST Micro Studio. Your own code you can write, or they will help you also. We are also taking help of the
Okay.
some kind of support to generate this kind
Okay.
of pattern. But I
Okay.
know the design, like you are telling now, unit cell I can able to see, and the multiple directions also. What is the reflection phase I am able to see. But how to put in this? So there is we have to routine, some code we have to write, and we have to attach macro we have to write.
Okay. Okay. Thank you. Thank you so much, sir. It was a
Yeah,
nice lecture, sir. Thank you.
yeah, thank you.
Mm.
Any other?
Dear participants, if you have any doubts, ask to sir. Okay, sir. I think all questions have been asked to you. What are the doubts they are having? It's
Yeah.
very nice lecture for us, sir. Being a at the stage of being initial stages in the PhD level, we are very much delighted to hear such kind of a lecture from you, sir. And we have learned we have learned from this session, from this lecture, how can we design metamaterial antennas, and how we need to do various parameters, how we need to consider the various parameters while designing the antenna. Thank you very much, sir. Thank you.
Yeah. Thank you. Thank you very much. So shall I close?
Yes, sir. Sure, sir.
Yeah. Okay.